Every knife in your kitchen, every spoon in your drawer, every sink, every pot, every bolt in a skyscraper. All of it exists because of one gray-green rock lying hundreds of feet underground, nickel ore. Without it, stainless steel wouldn't exist at all. Nickel is what transforms ordinary iron into metal that won't rust for decades. Add 8% nickel to steel, and it withstands seawater, acids, extreme temperatures. Every year, humanity mines 3 million tons of this metal. Value: $50 billion. But the journey from rock in the ground to shiny stainless steel sheet? It's technological hell. Explosions in quarries. Smelting at 2,700 degrees Fahrenheit. Chemical baths with sulfuric acid. Electrolysis under thousands of volts. How do you get metal that's 99.9% pure from gray rock that looks like an ordinary stone? Watch till the end. You'll see how the foundation of modern civilization is born. Planet Earth holds 300 million tons of nickel, but it's buried deep. The biggest deposits are in Indonesia, the Philippines, Russia, Canada, Australia, China, and the US. Not miners, processors and consumers. America uses it for aerospace and nuclear reactors, but it all starts in the pits. Open pit mines in Indonesia are wounds in the jungle the size of a city. A pit 1,000 feet deep, 3 miles wide. Excavators with 700 cubic foot buckets gnaw at the earth around the clock. The ore here is called laterite. It's a reddish-brown rock that looks like clay. Just 1 to 2% nickel. The rest? Iron, silicon, magnesium. But even these scraps of nickel make mining profitable. One Belazi haul truck carries 300 tons of ore out of the pit. 500 trips like that a day. 150,000 tons of rock daily. That's an entire mountain of material you need to squeeze metal from. The ore heads to primary processing. Here it's crushed and sorted. Massive jaw crushers grind car-sized chunks down to 4-inch pieces. The noise is so intense workers wear noise-canceling headphones. Then cone crushers pulverize the rock to gravel size. Mills with hardened steel balls turn the gravel into powder. Inside a 65-foot rotating drum, 4-inch steel balls hammer the ore. After 6 hours of spinning, the rock becomes dust. This dust gets mixed with water. You get a liquid slurry. It runs through magnetic separators. Nickel ore is weakly magnetic, but the iron in it magnetizes stronger. Some of the waste rock gets filtered out. Nickel concentration in the slurry jumps from 2 to 4%. Still not much, but better. The slurry thickens in huge settling tanks. Water drains away, leaving wet paste. It dries in drum dryers at 400 degrees. What comes out is dry concentrate, ready for smelting. From 1,000 tons of ore, you get 300 tons of concentrate. (1751). Swedish chemist Axel Kronstedt is studying a strange mineral from the Los Mine. The rock's reddish, looks like copper ore. Kronstedt tries to smelt copper from it, but gets a white metal unlike anything known. Hard, heavy, doesn't rust. He names it nickel, after Nickel the mountain spirit from German folklore who tricked miners by slipping them worthless rocks instead of copper. But nickel turned out to be anything but worthless. In the 19th century, they start adding it to steel. The British discover that 5% nickel makes battleship armor twice as strong. The Germans use nickel steel for artillery. World War I turns nickel into a strategic resource. Whoever controls nickel controls military production. In the 30s, metallurgist Harry Brearley invents stainless steel. The formula is simple: 18% chromium, 8% nickel, the rest iron. This steel never rusts. Revolution in kitchens, hospitals, factories. Demand for nickel explodes. The hunt for new deposits begins worldwide. The 1960s. Discovery of massive deposits in New Caledonia and Indonesia. Laterite ores containing billions of tons of nickel. But there's a problem. These ores can't be smelted the conventional way. Too many impurities, compositions too complex. New technology is needed. The Canadians invent the Sherritt-Gordon process. The Chinese develop a pyrometallurgical method called RKEF. Rotary kiln, electric furnace, ferrochrome. Every country creates its own nickel extraction methods. By the 2000s, China becomes the dominant processor. They build dozens of plants in Indonesia and the Philippines. Strategy's simple. Control the processing, control the market. The US took a different path. Americans focus on high-purity nickel for EV batteries and reactors. Smaller volumes, but the highest quality. A plant in Ontario processes Canadian ore using flash smelting technology. Temperatures above 2,900 degrees Fahrenheit. Metal purity, 99.999%. This nickel goes into Teslas and nuclear submarines. Two approaches, two philosophies. China wins through volume, America through quality. The smelting shop is the hottest place in the plant. In the center of the hall stands an electric furnace as tall as a 5-story building. Power output, 100 megawatts. That's like 10,000 homes running simultaneously. Nickel ore concentrate is loaded from the top along with coke and fluxes. Coke is pure carbon, the heat source. Fluxes, limestone and quartz, they bind the waste rock. Through graphite electrodes, they run a current of 100,000 amps. Voltage, 200 volts. Temperature inside the furnace climbs to 1,500 degrees in an hour. The ore melts. Heavy metals, nickel, iron, cobalt, settle to the bottom. Light slag floats to the top. This separation is critical. After 8 hours of smelting, the furnace is ready for tapping. A tap hole opens at the bottom. Molten metal flows through a channel into a ladle. It glows white-hot. Temperature 1,400 degrees. Workers in silver suits control the process remotely. One ladle holds 50 tons of metal. This is matte, an alloy of nickel, iron, and sulfur. Nickel content, 20%. That's not enough. Further refining is needed. They pour the matte into a converter, a massive horizontal barrel 50 feet long. Oxygen gets added too. The blow begins. Oxygen at 150 psi blasts into the molten mix through tuyères. The reaction's exothermic. Releases so much heat the temperature shoots up to 3,000 degrees without any external heating. Sulfur and iron oxidize, burn off. New slag forms, gets drained away. After 6 hours of blowing, what's left in the converter is fine matte, an alloy with 50% nickel. But even that's not pure enough for high-tech applications. Next stage, electrolysis. The fine matte gets ground into powder and dissolved in sulfuric acid at 180 degrees. You get a green solution of nickel sulfate. This solution goes into electrolytic cells. Each cell, a tank 10 feet by 7, 3 feet deep. Inside hang titanium anodes and nickel cathodes. Between them, the solution. They run a current at 2 volts, current strength, 20,000 amps per cell. Nickel from the solution plates onto the cathodes. Over a week, each cathode builds up a layer of pure nickel about an inch thick. They pull the cathodes out, scrape off the nickel. Purity, 99.95%. And just like that, after passing through explosions, crushing, smelting at temperatures above 2,700 degrees Fahrenheit, oxidation, dissolving in acids and electrolysis, a dull gray rock transforms into a shining metal that changed the world. Without nickel, there'd be no skyscrapers, their steel frames would rust away in years. No submarines, seawater would eat through their hulls. No nuclear reactors, their pipes couldn't handle the corrosive environment. Every component that needs to last decades in conditions where ordinary steel surrenders contains nickel. 3 million tons per year. 200 consumer nations. Thousands of factories, millions of jobs. Indonesia digs the ore, China smelts the metal, America turns it into superalloys for space. Europe stamps out stainless steel for hospitals. A closed loop that keeps civilization afloat. Nickel isn't just a metal. It's a guarantee of durability for everything we build. Proof that humans learn to take nature's dull rocks and turn them into eternity. Every time you wash your hands in a sink that gleams like new after 20 years of service, remember, that's nickel at work. The metal that conquered time and corrosion. Ready to explode with curiosity? In this video, we're throwing open the secret doors to the world of fireworks and firecrackers you never knew existed. Stick with us and you'll see how the magic of the brightest explosions is born from simple gunpowder. Discover the wild history of their creation and learn the unusual secrets of pyrotechnic masters. How do they create explosions in every color of the rainbow from ordinary black powder? Why can a single firework contain over 1,000 pellets, each burning its own unique color? What metals create red, green, and blue fire in the sky? And most importantly, why do masters remove even their wedding rings before work? And how can one stray spark destroy an entire lab? You'll find out how many hours it takes to create one professional firework, which countries produce 90% of the world's pyrotechnics, and what one epic New Year's Eve show costs. This story will make your heart race. Watch until the end, because the most important part is coming. Stay with us until the finale and you'll learn something that will flip your perspective. Don't miss it. Firecrackers. These are the more zippy guys in the pyrotechnic family. Their thing is sound, not spectacle. Even though they're simpler in design, they create the same magic, noise, and adrenaline. Like fireworks, the foundation of firecrackers is black powder, but here everything's a bit simpler. The main goal? Hit the right balance for a powerful bang without the extra special effects. Typically, a firecracker has a powder mixture, a casing, and a fuse. We'll talk about the filling later, but for now, let's learn a bit about the casing. It's a paper or cardboard cylinder that holds everything together. The material needs to be strong enough to contain the explosion until the moment of rupture, but not so strong that it creates dangerous shrapnel. The fuse is the most crucial element. It kicks off the explosive process. This could be a thin cotton cord soaked in chemicals, or more modern ignition mechanisms. The word firecracker comes from the French pétard, meaning explosion. Firecrackers, like fireworks, have Chinese roots. How do they make firecrackers? All components for the gunpowder mixture are carefully weighed and mixed to achieve the perfect consistency. Precision is critical here. Too much potassium nitrate and the explosion becomes uncontrollable. Too little and the firecracker won't ignite. Paper or cardboard tubes are cut to the required length, then filled with the gunpowder mixture. Typically, the casings have sealed ends to create the necessary pressure for detonation. At the top of the firecracker, they create a small opening where the fuse is inserted. It's secured using glue or special putty. The bottom and top edges of the firecracker are tightly sealed, usually with glue or heat sealing. This ensures safe storage and transportation. Next, firecrackers undergo rigorous testing. Manufacturers check sound levels, ignition speed, and blast quality. Not all firecrackers are created equal. Cheap firecrackers often have uneven filling, weak sound, and a higher risk of failure. They use lower quality materials like regular paper instead of cardboard. Quality firecracker casings are made from strong yet lightweight material. The gunpowder mixture is evenly distributed for a consistent effect. Fuses have precise burn times to give users enough time to move to a safe distance. Making firecrackers is no joke. Pyrotechnic factories have strict safety rules. Workers operate in small groups, wear anti-static clothing, and handle minimal amounts of mixture at any given time to reduce the risk of accidental explosions. Why are firecrackers so loud? This question often sparks curiosity. The thing is, a firecracker explosion isn't just a chemical reaction. It's the release of massive energy in a confined space. When gunpowder burns, it releases hot gases that rapidly expand, creating a powerful shock wave. And since a firecracker's casing is tightly packed, that wave is accompanied by the signature bang. Originally, firecrackers were used to scare off evil spirits, and only later did they become a popular form of entertainment. Making fireworks also requires mixing gunpowder with other components first. If gunpowder is the engine of the firework, then the other substances are the artists. They create the explosion of color, light, and shape. To create bright sparks, we need metal powders. That's aluminum, magnesium, titanium shavings. For vivid colors, they use metal salts like strontium, barium, copper, and sodium. Potassium nitrate, perchlorates, and charcoal amp up the explosive energy. After all, they're the oxidizers in fuel. And to hold all the components together, you need binding agents. Water-soluble glues, for example. Each component is first ground down into the finest powder. Imagine gleaming metallic particles dancing in the light as the craftsman preps them for mixing. The powders are so light, it's like they could just hang in the air like magic dust. The most important part begins when the ingredients go into the mill with ceramic or wooden balls. These balls rotate smoothly, grinding the mixture to perfect uniformity. The rustling and gentle tapping create their own rhythm, a sound that reminds you an explosion of colors is being born. When it comes to mixing ingredients by hand, traditional manufacturers approach the stage with reverence. Specialists carefully and slowly mix the ingredients with wooden or copper paddles. Why so slowly? Because even one accidental spark can trigger an explosion. The mixture looks like shimmering sand, where each component has its role. To prevent accidental explosions, the mixture is often moistened. Water doesn't just make the process safer, it adds mysterious alchemy as the gunpowder and dyes form tiny granules. The slightest mistake can lead to tragedy. You know what pyrotechnics masters do before starting work? They remove all metal objects, even rings, to avoid sparks. In many labs, cell phones are strictly banned, and clothing is chosen from anti-static materials. Even the air matters. Facilities maintain controlled humidity so the mixtures don't dry out and become explosive. Before packing the mix into a shell, craftsmen test how it burns. Flame bursts from a tiny sample and everyone in the room holds their breath. Will this be the perfect shade of blue? Are the sparks bright enough? It's like a dress rehearsal before the big show. Creating shapes and colors, that's the most exciting part of production. Want a heart or a star in the sky? It all depends on how the stars are arranged, those little pellets packed with special compounds. Where do those brilliant reds, greens, and blues come from? Chemical compounds. For instance, barium creates green, strontium gives you red, and copper produces blue. Once all the components are prepped, the next crucial step is loading the shell, where the heart of the firework comes to life. This is where the explosive mix and colorants transform into a finished product, ready to paint the night sky in every color of the rainbow. The shell is the casing that holds all the fireworks components together. It's made from a special material capable of withstanding high pressure and temperature, yet light enough to soar into the sky. Cylindrical shapes are perfect for creating crisp patterns like rings, chrysanthemums, or peonies. Spherical shapes create symmetrical and three-dimensional effects, like a ball exploding with hundreds of sparks. The process of filling the shell is extremely important, because proper component placement ensures the desired effect. First, they take cylindrical or spherical blanks, usually made from cardboard, plastic, or special paper soaked in fire-resistant substances. The sphere typically consists of two hemispheres that are later joined together. It's crucial that the shell be perfectly airtight. This guarantees the burst happens at the right moment and with the right force. The gunpowder charge, as the main propellant, is positioned in the center of the shell. It's responsible for lifting the firework into the air and detonating it properly. Colorants and specialty mixtures are placed around the charge. Each star element is laid by hand or with specialized machines. Star elements are the pellets that burn in the sky. For spherical shells, these stars are arranged evenly to form a perfect sphere when detonated. In cylindrical shells, charges are often layered or shaped into specific patterns, depending on the intended effect. One standard spherical firework contains an average of 200 to 300 pellets. In large multi-layered shells, there can be over 1,000. To ensure the firework detonates at the right moment, a delay fuse is added to the shell, a small tube filled with a special compound that burns slower. The timer connects to the main charge, providing a delay between the rocket's launch and the explosion in the sky. After all elements are positioned, they're secured with a bonding compound or paper dividers. This is crucial so none of the components shift during launch. The casing is additionally wrapped with strong thread or glue to give it rigidity. Producing a single large professional firework can take up to 4 hours considering the manual assembly and inspection. For a large-scale show with several thousand shells, pyrotechnicians work for several months. The spherical shape is a classic in pyrotechnics. It ensures even distribution of stars during the burst, creating the effect of a perfect circle. Filling such a shell requires even greater skill. Each star is manually positioned around the central charge, and here everything depends on the master. How the components are arranged is how the burst will look. For example, to create a smiley face in the sky, the pellets are laid out in the shape of a face. When the gunpowder explodes, the pellets scatter precisely in the shape of the intended pattern. Every year, the world produces over 200,000 tons of fireworks. The production leader is China. It accounts for roughly 90% of global output. For major holidays, such as U.S. Independence Day or New Year's in Sydney, up to 10,000 individual fireworks are launched in a single night. This can last over 20 minutes, and the cost of a single show sometimes reaches $5 million.
Every year, over 150 million cubic meters of plywood are produced worldwide, enough to have a train of wagons loaded with these sheets circle the Earth at the equator several times. But how is an ordinary tree trunk turned into this unique material, used in furniture, construction, and even shipbuilding? What secrets does the process hide? Starting with spa treatments for logs and ending with a hot press where layers of wood are permanently bonded into a monolith. Watch until the end and you'll learn about the secret pencil that remains after production and why it too has its own value.
It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, or pine. After delivery to the factory, the logs undergo the first and very important stage of preparation, hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours and sometimes a whole day. This kind of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible. After the bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface.
The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk like a scroll of ancient papyrus, turning a three-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor while hot air intensely blows on them from all sides. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks.
At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table, and on top of it, a sheet coated with glue. And here lies the main secret. Each subsequent sheet is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, and the third's lengthwise again. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split, and evenly distributes the load.
That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-story structure, between whose plates several dozen future plywood sheets are loaded simultaneously. With an enormous force reaching tens of kilograms per square centimeter, the plates compress the veneer layups. At the same time, the plates are heated to a temperature of 150 degrees Celsius. Under the influence of high pressure and temperature, the glue polymerizes, permanently bonding the layers into a single, incredibly strong monolith.
Hot sheets of plywood come out from under the press and are stacked for gradual cooling. After this, they undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, or glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a marking is applied to it. The finished stacks of plywood are sent to the warehouse to later become part of furniture, houses, and ships.
The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets.
The Caterpillar 3618 engine, 18 cylinders, 88 gallons of displacement, 7,200 kilowatts of power, 9,655 horsepower. One engine weighs 79,000 pounds. The piston in this engine, 11 inches in diameter, 11.8 inches of stroke, 50 pounds in weight. This is Caterpillar's largest piston. How do they make it from liquid aluminum? Today you'll see the complete production cycle of a giant piston, from an aluminum ingot to a part that moves at 33 feet per second and withstands 2,685 psi. If you want to see how they make the heart of a giant engine, subscribe to the channel. Here we show you the factories that move the world. The Caterpillar 3618 engine is designed for high-speed marine vessels, ferries, patrol boats, yachts. A single engine produces 9,655 horsepower at 1,050 revolutions per minute. It's a V18 four-stroke diesel. Cylinder bore is 11 inches. Stroke is 11.8 inches. Displacement per cylinder is 1,130 cubic inches. 18 cylinders total, 20,330 cubic inches. Compression ratio 12.6 to 1. Maximum cylinder pressure 2,680 psi. That's 185 atmospheres. Combustion chamber temperature 3,600 degrees Fahrenheit. Mean piston speed 34.4 feet per second. The piston travels 11.8 inches in 0.028 seconds. Up and down 1,050 times per minute. 70 million cycles over 10,000 hours of operation. The piston material has to withstand all of that.
The piston is made from an aluminum alloy. Aluminum is lightweight, density of 169 pounds per cubic foot. That's 3 times lighter than steel. Aluminum conducts heat well. Thermal conductivity of 133 BTU per hour per foot per degree Fahrenheit. That's 5 times better than steel. They use alloy 2618. Composition: 92% aluminum, 4% copper, 1.5% magnesium, 1% nickel, 1% silicon. Copper provides strength at high temperatures. Magnesium increases hardness. Nickel reduces thermal expansion. Silicon improves casting properties. The alloy arrives in ingots. Shape: a cylinder 12 inches in diameter, 3 feet 3 inches long. Ingot weight: 353 pounds. Before forging, the ingot is cut into blanks. Blank length: 12 inches. Weight: 84 pounds. This is the blank for one piston with extra material for machining. The blank gets loaded into an induction furnace. Temperature: 895 degrees Fahrenheit. Heat time: 30 minutes. The aluminum softens. Doesn't melt. Melting happens at 1220 degrees. We need plasticity for forging. The heated blank transfers to a forging press. Hydraulic press. Force: 10,000 tons. That's 100 meganewtons. The blank sits in the lower die. Die made from heat-resistant steel. The upper die descends from above. The press creates pressure. Aluminum flows, fills the die cavity, takes the shape of a piston. The process is called backward extrusion. Metal flows upward around the punch, forms the piston skirt. Pressure climbs to 10,000 tons. Forging time: 12 seconds. Metal densifies. Grains align along stress lines. This makes the piston strong. Forging increases strength 30% compared to casting. After forging, the press opens. Piston extracted. It's hot, 750 degrees. Weight: 66 pounds. Shape's close to final, but machining still needed. Heat treatment. The forged piston goes into the hardening furnace. Temperature: 986 degrees Fahrenheit. Hold time: 8 hours. Copper and magnesium dissolve into the aluminum. The structure becomes uniform. Then, rapid cooling in water. Water temperature: 68 degrees. Cooling rate: 180 degrees per second. Copper and magnesium don't have time to precipitate out. They're trapped in the lattice. Strengthening zones form. After quenching, the piston is soft. Hardness: 60 on the Brinell scale. Artificial aging is needed. The piston is heated again. Temperature: 374 degrees. Time: 16 hours. Copper and magnesium precipitate from the lattice as fine particles. They strengthen the aluminum. Hardness climbs to 135 on the Brinell scale. Strength reaches 65,000 pounds per square inch. Elongation: 10%. The piston is strong and ductile at the same time. Machining begins with the turning operation. The piston gets clamped into the chuck of a CNC lathe. The chuck diameter is 19.7 inches. Spindle speed is 300 revolutions per minute. The cutting tool is carbide, tungsten carbide. They machine the outer surface of the skirt. Final diameter is 11.02 inches. Tolerance, plus or minus 0.0008 inches. Skirt taper,
0.002 inches per inch of length. This compensates for thermal expansion. Cutting speed is 490 feet per minute. Feed rate is 0.008 inches per revolution. Depth of cut is 0.02 inches. They remove 0.28 inches from the diameter. Machining time is 20 minutes. The surface is smooth. Surface roughness is 63 micro-inches. Then they mill the ring grooves. 3 grooves. Width of the first is 0.16 inches. Second is 0.14. Third is 0.2 inches. Depth of the first is 0.31 inches. Milling cutter diameter is 4 inches. Spindle speed is 1200 revolutions per minute. Groove accuracy plus or minus 0.0004 inches.
They're drilling the hole for the piston pin. Hole diameter, 4.33 inches. Depth, 7.87 inches. Carbide drill bit. Rotation speed, 500 revolutions per minute. Feed rate, 0.006 inches per revolution. Drilling time, 8 minutes. After drilling, reaming. The reamer brings the diameter to 4.3302 inches. Tolerance, plus 0.0004 inches, minus 0. Surface roughness, 0.315 thousandths of an inch. This is an interference fit for the bronze bushing. The bushing gets press fit with 10 tons of force. Interference, 0.0012 inches. They mill the oil channels. 2 channels, diameter 0.47 inches, running from the crown to the skirt. They carry oil away for cooling. They drill the oil jets. Diameter, 0.079 inches. 8 of them around the crown circumference. Oil sprays through them onto the inner surface. Cooling is critical. Crown temperature hits 662 degrees Fahrenheit. The oil carries the heat away. Machining the combustion chamber. The piston crown gets milled on a 5-axis machine. The combustion chamber has a complex shape. A toroidal cavity, diameter 7.1 inches, depth 2 inches, chamber volume 0.3 gallons. The shape's optimized for mixing fuel with air. Ball nose cutter, diameter 0.8 inches. Spindle speed 3,000 revolutions per minute. Tool path spirals from center to edge. Spiral pitch 0.02 inches. Machining time 40 minutes. Surface roughness 0.00016 inches. Then chamber polishing. Abrasive paste, 3-micron grit. Polished with a felt wheel. Speed 1,000 revolutions per minute. Time 5 minutes. The polished surface prevents carbon buildup. Final operation, honing the skirt. Honing creates a crosshatch pattern of micro grooves. Angle 60 degrees. Groove depth 0.00012 inches. Width 0.0008 inches. These grooves retain the oil film, reduce friction. Honing time 10 minutes. Coatings and inspection. The crown gets a ceramic thermal barrier coating. Thickness, 0.3 millimeters. Material, yttria stabilized zirconia. Thermal conductivity, 2 watts per meter Kelvin. That's 100 times less than aluminum. The coating drops the crown temperature by 100 degrees. Applied by plasma spray. Plasma temperature, 10,000 degrees. Particle velocity, 1,000 feet per second. The skirt gets a graphite coating, anti-friction. Thickness, 0.015 millimeters. Cuts friction by 40%. Reduces wear at startup. Ring grooves get hard anodized. Hard anodization. Layer thickness, 0.05 millimeters. Hardness, 500 Vickers. Protection against ring wear. Every piston gets inspected. Diameter measured at 6 points. Laser micrometer. Accuracy, 0.001 millimeters. Weight gets checked. Scale accurate to 1 gram. Tolerance, plus or minus 5 grams. Weight variance in a set, no more than 10 grams. For engine balancing. X-ray checks internal defects, cracks, porosity, inclusions. Rejection rate, 0.5%. Finished piston weighs 51 pounds. Diameter, 11 inches.
Height, 13.8 inches. It'll run 10,000 hours, 70 million cycles. Handle temperatures of 350 degrees. Pressure, 185 bar. Speed, 33 feet per second. That's how Caterpillar makes the biggest pistons. From aluminum ingot to a component that holds 9,000 horsepower. If this was interesting, hit that like button. Comment what engines you know. Subscribe. Here we show you how giants get made.
Right now, 160 feet beneath London, in total darkness, a steel worm the length of an aircraft carrier is crawling forward. Inside it, a factory floor with conveyor belts, a cafeteria, toilets, and 40 engineers. The machine digs the tunnel it's traveling through. It lays concrete walls behind itself. It replaces its own teeth on the move. This is a TBM, a tunnel boring machine. The head with a cutting wheel as tall as a 6-story building. Total length of the whole assembly, 1,300 feet. Weight, 10,000 tons, like the Eiffel Tower lying on its side. One of these costs more than a 5th-generation fighter jet. And if it gets jammed in the rock, they won't retrieve it. They'll abandon it. Pour concrete over it and leave it there forever. Under London alone, 8 such machines are already buried. And there's one trick that lets a TBM chew through solid rock at 33 feet per day without stopping for a single second. I'll show you that trick right at the midpoint of this video. But first, let's go inside the steel worm. From the outside, it's just a round steel wall. You only see the machine's face. A black wheel, 56 feet across, studded with steel discs. That's the cutting edge. Beyond it, into the tunnel darkness, stretches a long tail of structures, rails, hoses, and systems. This is what a modern TBM looks like, a tunnel boring machine. Not a machine in the usual sense, more like an underground factory on wheels. It has its own hydraulics, its own power plant, its own conveyor system running for miles, its own crew. Total length, up to 1,300 feet. That's 4 football fields laid end to end, hidden underground. On the front wheel, dozens of cutter discs. These are thick steel rollers made of tungsten carbide, each one the size of a large stock pot, weighing 440 pounds. Each one costs as much as a new car. There are over 60 of them. The wheel turns slowly, 1 or 2 rotations per minute. Calm, impassive. But it's precisely this unhurried pace that's chewing through granite right now. And this is where things get really strange. Cutter discs don't saw rock, they crush it. The cutter head presses its entire machine weight into the face and squeezes the discs against the rock. Each disc takes 25 tons of load. That's the weight of a city bus, forced through a 2-inch steel ring. Under that kind of pressure, granite stops being stone. It becomes brittle, like a cracker. Cracks, chips off, crumbles into pea-sized bits. The wheel shaves off about 1 inch per revolution. Per shift, 16 to 24 inches of rock turned to rubble. Inside the machine, it sounds like a constant low growl. The walls vibrate. The air smells like hot iron and stone dust. In the operator's cab, screens show pressure on each of the 60 discs individually. If one disc breaks and stops transferring pressure, the neighbors get overloaded. Within half an hour, the TBM just loses its teeth. One lost disc, and the machine's down for a day. Every hour of downtime costs 80,000 euros. But that's only one task. The rock being cut has to go somewhere. Right behind the cutting wheel sits a massive funnel, the machine's shield. Everything the wheel chews up dumps in here. Next up, the conveyor belt. A long rubber belt, about 3 feet wide, runs through the entire TBM, backward through the whole 1,300-foot train all the way to the tunnel exit. In a single shift, 5,000 tons of rock travel down this conveyor. That's 200 dump trucks packed to the brim. 200 truckloads of underground debris every 12 hours. And that's just from one machine. If the rock's dry, the conveyor coughs up dust and rumbles with stones. If there's water at the face, behind the machine flows a real underground river of liquid mud. Pumps the size of houses stand by to pump it up to the surface. If they fall behind, the TBM starts to drown. And right now, as we speak, something that should be impossible is happening. The machine is simultaneously cutting rock and moving forward, pushing itself 10 meters a day. Here's how. ATBM has no wheels, no tracks, nothing that normally moves machinery. The machine moves forward only by pushing off its own tunnel. Sounds weird, but look. Around the perimeter of the body sit hydraulic jacks, about 20 of them, each one thick as a utility pole. Together, they can push with a force of 100,000 tons. That's the weight of 17 Eiffel Towers directed at a single point. With these jacks, the machine braces against the tunnel wall behind it, against the concrete rings already installed, and pushes itself forward, 2 inches, then 4, then 8. And here's the main trick I promised at the start. While the front head chews through rock, at the exact same time, in the rear section of the machine, a massive mechanical manipulator is working, the erector, a robot arm weighing 100 tons. It doesn't wait for cutting to stop. It grabs the next concrete ring and sets it in place simultaneously. The machine never stops. Cutting happens without a break. Tunnel assembly happens without a break. It's like a train laying track beneath itself without slowing down. That's exactly why a TBM pulls off its legendary 30 feet a day. The concrete rings that make up the tunnel aren't poured on site. They're prefabricated at a massive plant on the surface. Each ring consists of 6 or 7 massive segments. Each segment weighs 6 tons. Picture a vertical concrete wall 16 inches thick and as tall as a person. These segments move forward through the TBM on a special narrow-gauge railway, heading straight to the erector. A robotic arm grabs one segment with a vacuum suction cup and places it into position. Installation precision, 1 millimeter. Any more error and neighboring segments won't fit together. A bigger mistake and the ring will crack under the pressure of earth above it. And above it, several million tons of rock are pressing down. Each installed ring is immediately compressed between 2 neighbors, the old one and the future one. The concrete doesn't work in bending, only in compression, and in that state it can hold entire mountains above its head. 40 rings like this means 130 feet of finished tunnel. Immediately, the next batch of segments will roll along them forward to the erector. Every 3 to 4 miles, the cutter discs wear down to nothing. Sharp edges turn into smooth pucks. They have to be replaced. And this is the most dangerous part of the entire TBM operation. The wheel sits at the front of the machine, underground, under massive pressure from water and soil. You can't just pop open a hatch. A ton of liquid mud under pressure will come flooding in. So they use a hyperbaric chamber. Before replacement, the air in front of the wheel gets compressed to 5 atmospheres. That's the pressure of a submarine at 150 feet. 2 workers in specialized suits enter the chamber, go through airlock procedures, and end up right at the cutting wheel. They've got 15 cutters to swap out per shift. Time limit: a few hours. If the compressor fails, pressure drops, the face collapses. If a worker slips up, a sharp-edged disc weighing 450 pounds slides off and snaps bone like a twig. After the shift, reverse airlock, an hour of decompression. Otherwise, your blood boils from the inside. It's the work of divers underground. And this whole time, the TBM has to hit exactly where it's being steered. Not an obvious task. The machine travels blind through rock. It can't see daylight. No GPS works under 650 feet of earth.
Instead, laser targets. On each segment of a laid tunnel, there are reflectors. A laser theodolite constantly fires a beam at these points and calculates the machine's position within a fifth of an inch. On the control panel, the operator sees the actual trajectory and the calculated one. The slightest tilt of the head, and half a mile later, the TBM will emerge 30 feet off target. That's catastrophic.
Under the English Channel, the opposing British and French TBMs drove toward each other for 30 miles in total darkness, through rock beneath the seabed. And they met with a discrepancy of 6 inches, over 30 miles. That's like firing a rifle in New York and hitting a coin in Philadelphia. Underground precision. It's not a question of quality, but a question of whether the machine makes it back to daylight or not. When the tunnel's done, the TBM reaches the finish. And here's where things get weird. Most machines never come back. They're buried. At the very end of the route, crews prepare a side niche in advance, a short, dead end. The TBM drives in. The crew removes the cutter head, the most valuable electronics, and some of the hydraulics. That stuff gets hauled to the surface. Everything else, the 300-foot-long body, the conveyor, the erector, the motors, stays in the niche forever. The crew fills the machine with concrete and walks away. The reason? Cold, hard economics. To turn around and drag a beast like that back out, you'd have to rebuild its entire route in reverse. That costs more than making a brand new TBM. Under London, 8 of these machines are already buried. Under the Bosporus, 2. In the Alps beneath the Gothard, 4. Across Europe right now, dozens of buried TBMs lie underground. Each one, a steel tomb as long as an aircraft carrier, and no one will ever see them again. Every subway station you walk through, bored by a TBM. Every rail tunnel in the Alps. Every drainage collector under a major city. London's Crossrail, 26 miles. Gotthard in Switzerland, 35. Brenner between Austria and Italy, 40 miles. The longest tunnel in human history. Without TBMs, none of this exists. A modern city isn't just what you see above ground. It's also the dark miles of infrastructure where trains run, water and sewage flow, cables race. Each of these miles is impossible to dig by hand, only with a machine the length of an aircraft carrier, with its own workshop, its own cafeteria, and its own tomb at the end of the line. And if you want to see how they make those concrete rings themselves inside a massive open-air factory, check out the next video about tunnel segment production.
Today we're going on an incredible journey. From massive crankshafts that power ocean vessels to precision railroad components that keep millions of passengers safe. Settle in and let's dive into the mesmerizing world of industrial manufacturing. Here we're witnessing something truly impressive, the machining of a massive marine crankshaft weighing over 15 tons. This isn't your typical workshop project. These crankshafts are the beating heart of container ships and cruise liners, converting the explosive power of diesel engines into rotational motion that propels these ocean giants across our seas. The star of the show, a revolutionary vertical boring mill. Rising nearly 3 stories tall, this engineering marvel features a 20-foot diameter faceplate capable of machining parts up to 65 feet long. The machine's spindle delivers an impressive 1,600 horsepower while maintaining accuracy tolerances of just 4/10,000ths of an inch. That's thinner than a human hair. An advanced computer numerical control system coordinates up to 12 simultaneous axes, ensuring every cut is executed with mathematical precision. Watch as the massive crankshaft rotates at a carefully controlled speed of 15 revolutions per minute. Carbide cutting tools, each costing more than a luxury car, slice through hardened steel like butter. The cooling system pumps 500 gallons per minute of specialized cutting fluid, preventing thermal distortion while washing away chips that look more like metal ribbons. Notice how the operator monitors vibration sensors and thermal cameras. At this scale, even tiny deviations can spell disaster. The real magic happens during the finishing passes. Using diamond-tipped tools, surface finish reaches an incredible 0.4 microns, smoother than a mirror. Laser measurement systems continuously verify dimensions, while ultrasonic testing ensures the internal structure remains intact. This single crankshaft will operate for decades, generating millions of horsepower cycles. It's a testament to German engineering precision that transforms raw steel into a mechanical masterpiece worth over $500,000. Welcome to where they've redefined what heavy-duty really means. This isn't just another CNC lathe. This is a mechanical monster engineered to tackle the roughest, toughest machining jobs in heavy industry. When aerospace manufacturers need to machine titanium landing gear components, or when power plants require custom turbine shafts, this is where they turn. This beast can handle parts up to 5 feet in diameter and 40 feet long, weighing up to 25 tons. The main spindle generates 400 horsepower through a precision planetary gearbox, delivering massive torque at low speeds. Watch the machine attack this massive steel workpiece with aggressive roughing cuts. The cutting parameters are mind-blowing. Depth of cut just over ½ an inch, feed rate around a 32nd of an inch per revolution, removing over 200 cubic inches of material per minute. High-pressure coolant jets at 1,000 pounds per square inch blast away continuous ribbons of steel chips that could fill a pickup bed in just minutes. Advanced vibration damping and thermal compensation systems maintain dimensional accuracy within 0.02 of an inch across the entire part length. The CNC system with adaptive control technology automatically adjusts cutting parameters based on real-time force and temperature feedback. It's like having a master machinist intuition built right into the machine's brain. Step into the world of railroad wheel manufacturing, where safety and precision aren't just priorities, they're matters of life and death. Every single day, millions of passengers trust their lives to these wheels, which must withstand enormous forces, extreme temperatures, and millions of rotation cycles. From high-speed trains racing across the European countryside to heavy freight locomotives hauling cargo across the American plains, the wheels we're about to see represent the culmination of over 150 years of railroad engineering evolution. Our journey begins with carefully selected steel billets, heated to a blazing 2,190 degrees Fahrenheit in massive induction furnaces. Watch as the glowing steel is shaped by 8,000-ton forging presses that deliver forces equivalent to the weight of 800 elephants. This forging process aligns the steel's grain structure, creating the incredible strength needed to support railcars weighing 25 tons. The wheels are then normalized in computer-controlled furnaces, cooling slowly over 48 hours to achieve the perfect balance of hardness and toughness. Quality control begins immediately. Ultrasonic testing reveals any internal defects that could prove catastrophic in service. Now the precision work begins. Each wheel blank is mounted on state-of-the-art CNC wheel lathes, masterpieces of German engineering capable of maintaining tolerances tighter than the thickness of paper. These machines feature massive chucks 10 feet in diameter that grip the wheel with hydraulic pressure equivalent to 50 car jacks. The cutting tools are specially designed carbide inserts, each costing $200 and engineered to maintain sharp edges through thousands of cuts. Computer vision systems scan each wheel, creating a three-dimensional map that guides the machining process. This is where artistry meets engineering. The wheel profile isn't just a simple curve, It's a complex mathematical shape that determines how the train will ride, steer, and brake. Watch as the lathe creates the tread surface with its precise 1 in 20 taper, the flange that keeps the train on the rails, and the intricate root radius that prevents stress concentrations. Each cut is monitored by laser sensors measuring to within 0.01 millimeters. Surface finish must be perfect. Any imperfections will create wear that could lead to derailment at 200 miles per hour. Here we're looking at one of the most demanding machining operations out there, boring and facing an 8-inch diameter hole through massive steel components. This isn't your typical drilling operation. We're talking about creating precision holes through materials that could stop a tank round. These operations are common in heavy industrial applications like hydraulic cylinders for mining equipment, deep hole drilling for oil drilling, and cylinder blocks for massive diesel engines. The horizontal boring mill dominates this operation with its massive spindle assembly, capable of reaching several feet into the workpiece. The boring bar itself, a precision tool weighing hundreds of pounds, must remain absolutely rigid while cutting forces try to deflect it. Advanced vibration damping systems and precision spindle bearings ensure cutting tool stability. The cutting insert, $300 of carbide engineering, must maintain a sharp edge while removing cubic inches of steel per minute. Watch as a massive cutting tool begins its journey through steel, creating this perfect 8-inch hole. The cutting parameters are carefully calculated. Too aggressive, and the boring bar will deflect. Too conservative, and productivity suffers. High-pressure coolant floods the cutting zone, not just for cooling, but to flush away the continuous stream of steel chips that could jam the operation. The machine's computer numerical control system automatically compensates for boring bar deflection, ensuring the final hole diameter stays within a tolerance of 0.01 inches across its entire length. Now comes facing, creating a perfectly flat surface perpendicular to the hole. The facing head, equipped with multiple cutting inserts, machines the surface at feed rates measured in thousandths of an inch. Once complete, this component could become part of a mining excavator's hydraulic cylinder, where it'll control movements of machinery weighing hundreds of tons. The precision we just witnessed ensures these systems run reliably for decades, moving mountains one bucket at a time. Our final segment showcases the artistry of complex turning operations, creating intricate threaded components that combine multiple diameters, sophisticated geometries, and precision threads in a single setup. These parts might look simple, but they represent the pinnacle of machining mastery, demanding perfect coordination of cutting tools, spindle speeds, and feed rates to achieve dimensional perfection across every feature. This component features multiple turned diameters, each with different tolerances and surface finish requirements. Notice the stepped geometry requiring different cutting tools for each operation, the internal threading that must align perfectly with external features, and the complex radii that seamlessly blend surfaces. The threading operation demands specialized thread cutting tools and precise spindle synchronization. The computer numerical control system coordinates spindle speed with carriage speed to create perfect thread pitch. Tool changes happen automatically, each cutting insert optimized for its specific operation. Single-point threading tools carve helical grooves with mathematical precision, creating threads that will mate perfectly with corresponding components. Thread pitch accuracy within 0.0001 inches, correct thread form angles, and perfect surface finish all combine to create threads exceeding commercial standards. The completed part undergoes comprehensive quality inspection using specialized thread gauges, optical comparators, and coordinate measuring machines. Every dimension, thread specification, and surface finish gets verified against engineering drawings. These complex turned parts often become critical components in aerospace applications, medical devices, or precision instruments, where failure isn't an option.
Every year, enough glass fiber rebar is produced worldwide to challenge the dominance of steel itself. This isn't science fiction, it's modern manufacturing. The world spends billions fighting rust, repairing bridges and car parks destroyed by corrosion. But there is a solution. A composite material that is twice as strong as steel, 4 times lighter, and simply does not know the meaning of the word rust. The market for this material is growing at 12% a year, and today you will see how hundreds of bobbins and a barrel of resin give birth to the building material of the future.
It all begins at one end of a vast workshop, in front of a structure that looks like a giant library for thread. It's called a creel. On a wall several meters high, hundreds, sometimes thousands of huge bobbins are mounted in neat rows. Wound onto each one is a fine glass thread, or roving. This isn't the glass from your windows. It's a special glass fiber produced by melting glass and drawing it through microscopic holes. The result is a thread thinner than a human hair, but with incredible tensile strength. This will be the skeleton. From each of these hundreds of bobbins, a single separate thread is drawn, and they all converge into one thick, fluffy bundle.
This river of glass fiber now begins its journey. It passes through a system of guides and tensioners. Each of the thousands of threads must be held at exactly the same tension. If one thread sags while another is too tight, the load in the final product will be distributed unevenly, compromising its strength. The dry glass bundle is then slowly submerged in a bath filled with a thick, sticky, honey-like liquid. This is the polymer resin, the flesh that will be built upon the glass skeleton. It's a complex chemical cocktail. The base is typically a polyester, vinyl ester, or epoxy resin. To this, a hardener is added, a catalyst that will trigger a chemical reaction, turning the liquid into a solid plastic.
Various additives can also be mixed in. Pigments for color, UV inhibitors to protect the rebar from sunlight, and fire retardants. The purpose of this bath is to impregnate every single tiny fiber. The bundle must be completely saturated in the resin, leaving no dry spots. Now heavy and soaked in sticky resin, the bundle emerges from the bath and heads towards the point of its creation, the forming die. This is the heart of the entire process. Imagine a thick steel plate with the perfectly round, polished hole, its diameter precisely matching that of the future rebar. The die is heated to a specific temperature.
As the wet bundle is pulled into this hole, several things happen at once. First, the die acts like a press, squeezing out all excess resin. Second, it compacts all the glass fibers tightly together, forming a perfectly round rod. Third, the heat from the die initiates the first stage of the curing reaction. Emerging from the die, we can already see the familiar shape of a rebar, but it is still soft and vulnerable. So how does it get its famous ribbed surface? Immediately after the die, while the rod is still hot and pliable, a special glass fiber strand is wound around it.
A thin resin-soaked thread is wrapped in a spiral around the surface of the rod, creating the textured pattern. The formed and wrapped rod now enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber which can stretch for dozens of meters, where a high temperature, typically around 200 degrees Celsius, is maintained. Here, the final transformation occurs. This isn't just drying. Under the heat, the resin molecules begin to rapidly link together, forming a strong, rigid, three-dimensional grid. The liquid, sticky syrup turns into an exceptionally strong and hard composite material, permanently bonding millions of glass fibers into a single, monolithic rod. As the rebar moves slowly through this hot tunnel, it acquires its final, rock-hard strength.
But what is pulling it through this long journey? At the end of the line sits a special pulling device. It typically consists of two caterpillar track mechanisms like those on a tank, positioned one above the other. They gently but very firmly grip the finished solid rebar and pull it towards them at a constant, precisely controlled speed. It is this machine that provides the force to draw the glass fibers through the resin bath, the forming die, and the oven. The speed of this movement is one of the most critical parameters controlling the quality of the final product. And so, from the other end of this long production line, an endless, perfectly straight, hard and hot GFRP rod emerges. The final act is cutting. An automatic saw is mounted across the line. It synchronizes with the speed of the moving rebar, and at the right moment, it makes a quick forward dash, and with a sharp whiz, it cuts a standard length, for example 6 or 12 meters, from the continuous rod. It then returns to its starting position. The finished, still warm rebars roll onto a cooling table, after which they are collected into bundles, tied, and sent to the warehouse. And so, before our very eyes, thousands of fragile glass threads and a barrel of sticky liquid have journeyed through baths, presses, and ovens to become the lightweight yet incredibly strong building material of the future.
The market for glass fiber rebar isn't yet a giant like the steel market, but it is the boldest newcomer, rapidly gaining traction. The global market for this material is already valued in the hundreds of millions of dollars, with staggering forecasts. It's expected to grow by 10 to 12% annually. Now for the key features that are making the steel industry nervous. The first and most obvious is weight. GFRP rebar is roughly 4 times lighter than steel of the same diameter. Imagine a lorry. It can deliver 4 times more GFRP rebar in a single trip than it could steel.
On the construction site, 2 workers can easily carry entire coils of GFRP rods, whereas moving steel requires a crane. This represents a colossal saving in logistics and labor. Second is strength.
And here, GFRP steps into the ring and knocks steel out in the first round. Its tensile strength is approximately twice that of standard steel rebar. This means that for some structures, a smaller diameter rebar can be used, saving even more on weight and volume. But the ultimate advantage, the true superpower of GFRP, is its war on rust. The main enemy of any reinforced concrete structure, from bridges to car parks, is not the load, it's rust. Water and salts penetrate through microcracks in the concrete, reach the steel rebar, and it begins to corrode. Rust expands in volume and literally bursts the concrete from within. And GFRP? It simply laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means the lifespan of the structure increases dramatically. A concrete structure reinforced with steel is designed for about 50 years. A structure with GFRP rebar can easily be designed for a lifespan of over 100 years.
Take up a stone. Bright red, heavy, looking like dried blood. It doesn't smell, doesn't burn, doesn't radiate. Just a beautiful mineral. Now throw it into a furnace at 1300 degrees Fahrenheit and liquid metal flows out. Silvery, heavy, cold to the touch. The only metal on Earth that stays liquid at room temperature. Mercury. A substance that has mesmerized alchemists for millennia, poisoned kings, and powered industry. And it's extracted from a stone that looks like a gemstone, but is actually just ordinary sulfide. Today, we're at a mine and processing plant where red rock turns into liquid silver. If you're into deep dives like this, subscribe and hit the bell so you don't miss new episodes. This red rock is called cinnabar, mercury sulfide, one of the few natural compounds where mercury shows up in Earth's crust. The chemical formula is simple: one mercury atom, one sulfur atom. Basically, nature locked liquid metal inside a sulfur cage, and to get it out, you've got to break that cage with heat. If you crack a chunk of cinnabar, the fracture surface reveals crystals with a diamond-like shine. The beauty's deceptive because the powder from this mineral is poisonous. Cinnabar was known even in ancient times. Egyptians used it as pigment, Romans painted palace walls with it, and Chinese alchemists believed the red ore was the key to immortality. Deposits are scattered across the planet, but the main ones are in Spain, Slovenia, China, and Kyrgyzstan. The Spanish mine at Almaden operated for nearly 2,000 years and gave the world more than a third of all mercury ever extracted. The ore sits in volcanic activity zones because mercury rises with hot solutions from deep within Earth's crust and settles in rock fractures as bright red veins. Sometimes cinnabar is so rich that the rock looks like someone painted it with scarlet dye. Mining starts underground. Miners drill into the rock with pneumatic jackhammers, place charges, and blast, bringing the whole face down. They load the ore into mine cars and haul it to the surface. It's hard, dangerous work. Even down in the mine, mercury vapor seeps from the rock, so ventilation runs at full blast. Mercury content in the ore is usually low, 1 to 12%. The rest is waste rock, sandstone, clay, quartz. But even 1% is worth going after because mercury fetches a high price. At the surface, the ore gets crushed in jaw crushers. 2 steel jaws squeeze the rock, breaking it down to gravel size. Then, vibrating screens sort the pieces by size. The fines go straight to the furnace. Oversized chunks loop back for another round of crushing. Dust is a whole other problem. It carries mercury, and breathing it is dangerous. So the crushing plant runs heavy exhaust and wet dust suppression. Workers wear respirators, and at the entrance, there's a mercury vapor monitor. If the needle swings into the red, they shut down the plant and air it out. Now comes the most critical step, roasting. The principle is simple yet brilliant. Heat cinnabar to 1100 to 1300 degrees Fahrenheit in air, and the sulfur bonds with oxygen and escapes as sulfur dioxide gas, while the mercury vaporizes. Two substances locked in stone for millions of years part ways forever, one into the air, the other into a pipe. Roasting furnaces come in different designs, but the classic is a rotary kiln. Picture a massive steel drum, 60 to 100 feet long, set at a slight angle. Ore gets fed in from the upper end, burners fire from the lower. The heat inside is so intense, the furnace walls glow a dull cherry red. The kiln rotates slowly, tumbling the ore, gradually pushing it downward as it heats up more and more. When the temperature hits the sweet spot, the cinnabar breaks down. Sulfur burns with a bluish flame, and mercury vapor, invisible and deadly, rises and travels with the flue gases into the condensation system. The spent rock, now stripped of mercury, spills out the lower end of the furnace into a waste pile, gray, lifeless, having surrendered everything valuable to the fire. Condensation is the moment when invisible vapor transforms into that actual liquid metal. Gases from the furnace pass through a long system of pipes and chambers that gradually cool down, usually with water fed through jackets on the outside. Mercury condenses first. Its boiling point is only 675 degrees Fahrenheit, so when the gases cool below that mark, silvery droplets start settling on the condenser walls. They trickle downward and collect in receivers, steel or ceramic containers. The sight is mesmerizing. From the pipe, as if from nowhere, heavy silvery liquid drips down, falling into the collector with a distinctive, soft sound. Not a clang, not a thud, but something in between. Because mercury is viscous and heavy, 13.5 times heavier than water. A quart of mercury weighs more than 28 pounds. Try picturing a quart of milk that weighs as much as a bucket of cement. The raw mercury from the condenser isn't ready for sale yet. It's swimming with impurities, soot particles, water droplets, traces of other metals. It's cleaned in several stages. First, they filter it through chamois leather or special fabric. Mercury passes through the pores while the dirt stays behind. Then, they wash it with diluted nitric acid, which dissolves impurities like zinc, lead, and tin, leaving the mercury itself untouched. The final purification is vacuum distillation. Mercury gets heated in a vacuum, where it evaporates at a lower temperature, while impurities with higher boiling points remain at the bottom. They collect the condensate, and now you've got mercury at 99.9% purity. It's poured into standard steel flasks holding 76 pounds. That's the international standard called a flask. The container's small, about the size of a thermos, but lifting it one-handed? Not easy. All because of that incredible density. Safety at a mercury plant is a world unto itself. Mercury vapor has no color and no smell, but it's extremely toxic. Just a few hours of breathing it can give you serious poisoning. Chronic exposure destroys the nervous system. That's why hatters in the 19th century went mad. They used mercury to treat felt and inhaled the fumes for years. Hence the phrase, mad as a hatter. In a modern plant, the entire facility operates under negative pressure. Air is constantly pulled inward, not pushed outward, so vapors don't escape into the atmosphere. Floors are coated with a special non-porous covering. If mercury spills, the droplets won't roll into cracks, but stay on the surface where they can be collected with a specialized vacuum or a sulfur trap. Sulfur powder binds mercury into harmless sulfide. Every worker carries a personal dosimeter that measures accumulated vapor exposure per shift. Exceed the limit, and you're pulled off the floor until your levels normalize. Where does all this mercury go? Historically, the biggest consumer was gold mining. Mercury dissolves gold, forming an amalgam. You then heat it up, and the gold evaporates out. Conquistadors in South America used this method, and it's exactly why the Spanish crown exploited almaden for centuries. Today, amalgamation is officially banned in most countries because of the catastrophic environmental damage. But in artisanal mining across Africa and Southeast Asia, millions of prospectors still use it. Poisoning rivers, poisoning soil. Other applications: chlor-alkali industry, thermometers, barometers, mercury lamps, electrical switches, catalysts. But the world is slowly moving away from mercury. In 2013, the Minamata Convention was signed, named after a Japanese city where, in the 1950s, thousands of people suffered devastating poisoning. Mercury leaked into the bay from a chemical plant. It built up in fish. And the people who ate that fish started losing their sight, their hearing, their coordination. The Minamata tragedy became a symbol of mercury pollution for decades to come. Mercury production worldwide is plummeting. Back in the mid-20th century, mines pulled out up to 10,000 tons a year. Now, less than 2,000. Most mines have shut down. The famous Almadine in Spain stopped operations and turned into a museum. These days, mercury increasingly comes from recycling, old thermometers, lamps, industrial waste. But humanity can't completely abandon it yet. Some chemical and electrochemical processes simply have no substitute. When you stand next to a flask where this heavy, silvery liquid sloshes around, it's hard to believe that an hour ago it was part of a red rock that sat underground for millions of years. Cinnabar guarded mercury like a safe guards valuables, and only fire could pick that lock. An ancient process, simple at its core, dangerous in execution, and still without an alternative.
Right now, 430 nuclear reactors are running on this planet. They light up cities, power factories, move aircraft carriers. But at the heart of every single one, a metal that can ignite a city or wipe it off the map: uranium. Just 1 kilogram of enriched uranium holds the energy of 2 million kilograms of coal. But how does this deadly element transform from gray ore into a gleaming fuel rod? You'll find out why miners wear dosimeters even in the shower, how centrifuges spin faster than a bullet, and what happens when a single uranium atom splits in two. Stick around to the end, because the finale shows how humanity tamed the power of the stars.
The story of uranium began long before the atomic age. In 1789, German chemist Martin Klaproth isolated a strange heavy metal from a mineral and named it after the planet Uranus, discovered just a few years earlier. Back then, nobody knew that this silvery gray element would become the most dangerous and most valuable material of the 20th century. In the 19th century, uranium was used to dye glass bright yellow and green colors. Uranium glass glowed under ultraviolet light and was considered a fashionable decoration. People didn't even suspect they were holding a potential bomb in their hands. Everything changed in 1938 when Otto Hahn and Fritz Strassmann discovered uranium nuclear fission. It turned out that a single uranium-235 atom, after absorbing a neutron, splits into two parts, releasing enormous energy and new neutrons. These neutrons can split the next atoms. That's how a chain reaction begins.
The world realized uranium isn't just a metal, it's the key to unprecedented power. The uranium race was on. The Manhattan Project in the US, Soviet programs, British developments, everyone was hunting for uranium deposits. And they found them. The largest uranium mines are located in Kazakhstan, Canada, Australia, and Namibia. Kazakhstan is the absolute leader, producing about 40% of the world's uranium. Canadian mines in the Athabasca Basin contain some of the richest uranium ores on the planet, up to 20% uranium versus the typical 0.2%. Australia's Olympic Dam deposit is so massive that its reserves are estimated in the millions of tons.
And in Namibia, the Rossing uranium mine is one of the world's largest open-pit operations, where giant excavators work around the clock. Every year, the world mines about 53,000 tons of uranium. Sounds like a lot, but uranium is actually a rare element.
In Earth's crust, there's just 2.8 parts per million, 1,000 times less than zinc and 40 times less than lead. Uranium mining starts deep underground, or on the surface of massive open pits. Underground mines plunge down to nearly a mile deep. Eternal darkness reigns here, sliced by beams from headlamps on miners' helmets. The air is heavy, humid, saturated with the smell of explosives and dust. Temperatures hit 104 degrees. At this depth, the rock heats up from Earth's core. Miners drill holes into the uranium vein, pack in explosives, and retreat to a safe distance. The blast roars like underground thunder, and tons of rock come crashing down. Massive loaders with wheels as tall as a person scoop up the debris and haul it to the mine shafts. Uranium ore isn't pure uranium. It's rock containing just 0.1 to 20.
The rest is waste rock, but even that tiny fraction makes every stone radioactive. The dosimeters on miners' belts click constantly, measuring radiation levels. Each worker gets a strictly limited radiation dose per year. Go over the limit, you're headed home until next season. At the surface, they load the ore into dump trucks and haul it to the processing plant. That's where the first stage of turning rock into fuel begins. They crush the ore in giant mills, where steel balls the size of watermelons grind the rocks into fine dust. This dust gets mixed with sulfuric acid. Chemical leaching starts. The acid dissolves the uranium oxide, leaving the waste rock untouched. What you get is a yellow-green liquid that looks like poisonous soup. They filter it, purify it, evaporate it, and what comes out is a bright yellow powder they call yellow cake. It's uranium concentrate, containing up to 80% uranium oxide.
Yellow cake gets packed into steel drums, 440 pounds each, and shipped to a conversion facility. But this uranium isn't reactor ready yet. The problem? Natural uranium is made of two isotopes, uranium-238, 99.3%, and uranium-235, just 0.7%. Only uranium-235 can sustain a chain reaction. So the uranium needs to be enriched, boosting the uranium-235 share to 3 to 5% for reactors, or up to 90% for weapons. At the conversion facility, yellow cake gets turned into a gas, uranium hexafluoride. This gas is poisonous, corrosive, and radioactive all at once. At room temperature, it's solid, like ice, but heat it to 133 degrees Fahrenheit and it turns straight into gas, skipping the liquid phase entirely. Uranium hexafluoride gets pumped into steel cylinders and trucked to an enrichment plant.
Here's where the most technologically complex stage begins: isotope separation. Uranium-235 and uranium-238 are chemically identical, but differ in mass by just 3 neutrons. How do you separate things that are almost the same? Gas centrifuge method. Picture a massive hall the size of a football field, packed with thousands of vertical metal tubes about 6 feet tall. These are centrifuges. Each one spins at speeds up to 100,000 revolutions per minute, faster than a speeding bullet. Uranium hexafluoride gets fed into the centrifuge, and under monstrous centrifugal force, the heavier uranium-238 gets thrown toward the walls, while the lighter uranium-235 concentrates in the center. The difference is microscopic, just 1% per pass. That's why the gas runs through thousands of centrifuges, connected in cascades. Each successive centrifuge receives slightly more enriched uranium than the one before.
The process takes months. Eventually, you get enriched uranium hexafluoride with uranium-235 content ranging from 3 to 5%. That's enough for a nuclear power plant. If you keep enriching it up to 90%, you get weapons-grade uranium. That's exactly why enrichment facilities are guarded better than fortresses. The enriched uranium hexafluoride is transported back to a facility where it's converted from gas into solid uranium oxide, a dark gray ceramic powder. This powder is pressed into small cylindrical pellets, about the size of a fingertip. Each pellet weighs around 7 grams, but contains energy equivalent to 400 kilograms of coal or 3 barrels of oil. The pellets are sintered in furnaces at temperatures of 1700 degrees Celsius. They become hard as diamond and develop a distinctive metallic luster.
Now these pellets need to be turned into fuel rods. They're loaded into long, thin tubes made from a zirconium alloy, a material that doesn't absorb neutrons and can withstand the extreme temperatures and pressures inside a reactor. Each tube is about 13 feet long and holds several hundred pellets. The tubes are hermetically sealed and assembled into bundles, fuel assemblies. A single assembly contains anywhere from 100 to 300 rods, held together in a unified structure with gaps for water circulation. One fuel assembly weighs up to 1,500 pounds. The finished fuel assemblies are shipped to nuclear power plants. Here, they're loaded into the reactor core, a massive pressurized steel vessel surrounded by walls of concrete and steel over 3 feet thick. When the rods are lowered into the reactor and the chain reaction begins, temperatures inside reach about 570 degrees Fahrenheit.
Neutrons tear through the reactor core, slam into uranium-235 atoms, split them apart, and each split unleashes massive energy. That energy heats water into steam. Steam spins turbines, turbines drive generators, and generators produce electricity that lights up millions of homes. A single fuel rod runs in the reactor for 3 to 6 years. During that time, it cranks out as much energy as an entire freight train loaded with coal or a tanker full of oil. But gradually, the uranium-235 burns out, and fission products pile up, radioactive isotopes that poison the reaction. The rod gets pulled from the reactor and dropped into a spent fuel pool, a massive tank of water 40 feet deep. Water cools the rods and absorbs the radiation. They'll sit here for years, cooling down and losing activity before they're shipped off for reprocessing or burial.
The entire journey of uranium, from a dark mine deep in the earth to a glowing reactor, is a story about how humanity learned to extract energy from the very heart of matter. From explosions in mine shafts to spinning centrifuges, from ceramic pellets to fuel assemblies, every stage demands precision, technology, and control. Uranium isn't just a metal. It's a bridge between the past, when we burned wood, and the future, when we might master nuclear fusion. Today, nuclear power provides about 10% of the world's electricity. That means every 10th light bulb on the planet shines because of uranium. But it's also a metal capable of destroying civilization in minutes. And as long as humanity holds this balance between creation and destruction, between light and darkness, we continue to exist. Uranium gave us incredible power, and now our job is not to abuse it.
What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, then gets reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore flare up like tiny controlled earthquakes. Zinc, the fourth most consumed metal in the world after iron, aluminum, and copper. 12 to 13 million tons of zinc are produced every year. 60% of all zinc goes into galvanizing steel. Without it, bridges, cars, and buildings would rust many times faster. But here's the shocker. At 2,700 degrees Fahrenheit, zinc literally turns into vapor and disappears into the air, and then condenses back into liquid metal. In this video, you'll learn things you never suspected, and at the end, the main secret will be revealed that will forever change how you think about zinc.
Picture a massive underground mine somewhere in China, Australia, or Peru, the world's biggest zinc producers. These are entire underground cities stretching hundreds of feet, sometimes even miles beneath the Earth's surface. We're not talking about simple holes in the ground. This is a network of tunnels, shafts, ventilation systems, and lift shafts. Powerful drilling rigs bore holes into the rock, blast holes. Explosives get packed into these holes. After a carefully controlled blast, massive volumes of rock break apart. It's like a spectacular but controlled earthquake in miniature. Dusty air gets quickly cleared by powerful ventilation systems, which also pump fresh air down to these depths. The broken ore then gets loaded onto massive underground trucks or conveyor belts using front-end loaders. It's a genuine underground transportation flow, continuously moving, hauling tons of ore to the central lift shafts. From there, the ore rises to the surface using powerful elevators or specialized conveyor systems, climbing hundreds of feet straight up.
At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock, containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a concentrator plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore into crushers that, with a deafening roar, break them down into smaller pieces. Then this crushed ore moves into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore is ground down to an extremely fine powder, almost like flour. This is critically important to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder is mixed with water and special chemical reagents in large tanks called flotation cells.
These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. The zinc mineral particles latch onto these bubbles and rise to the surface, forming foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can contain up to 60% zinc. Since zinc is often found alongside lead, the processing plant may run multiple flotation cycles to separately extract zinc concentrate from lead concentrate. The zinc concentrate you end up with still isn't pure metal. It has to go through metallurgical processing to get metallic zinc. And now we enter the world of extreme temperatures. If the pyrometallurgical method is used, the zinc concentrate first undergoes roasting. The concentrate is heated in specialized furnaces at temperatures around 1800 degrees Fahrenheit.
This removes the sulfur, which is part of the sulfide ore, converting it into zinc oxide. The sulfur transforms into sulfur dioxide gas, which is captured and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable product. Next, the zinc oxide is mixed with coal and heated to even higher temperatures, over 2200 degrees Fahrenheit,
sometimes even 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process occurs. The carbon strips oxygen away from the zinc oxide, freeing up pure metallic zinc. And this is where that incredible wow moment of vaporization happens. At these temperatures, the metallic zinc transitions into a gaseous state. It evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is significantly higher, zinc literally turns into vapor, which rises and gets collected in specialized condensers.
The vapor cools and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or granules. Now for the history. Zinc has been known to humanity for thousands of years, though it was only isolated as a distinct metal in the 16th century. Ancient civilizations used brass, an alloy of copper and zinc, without knowing it actually contains zinc. In India and China, people learned to smelt zinc as far back as the Middle Ages. But modern industrial zinc production only began in the 19th century with advances in smelting technology. The primary use of zinc: galvanizing steel. Around 60% of all zinc produced goes toward protecting steel from corrosion. Zinc coating on steel creates a sacrificial layer. The zinc oxidizes instead of the iron, protecting the structure. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a surge in resource demand.
(15 to 20% of zinc goes into making alloys like brass and die-casting alloys. These alloys end up in car parts, home appliances, toys, plumbing, and electronics. Another 10 to 15% becomes zinc oxide and other chemical compounds. Zinc oxide has crazy wide applications: sunscreens and cosmetics, paints, ceramics, rubber manufacturing, and even livestock feed supplements. Its antibacterial and protective properties make it a universal ingredient. The rest of the zinc gets used in batteries, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, because zinc is absolutely vital for the human immune system. As for prices, like most commodities, zinc prices swing with global supply and demand, economic cycles, and what's happening in the biggest producer and consumer countries. Yet demand for zinc remains steady or growing, driven by urbanization, infrastructure development, and the need to protect metals from corrosion worldwide. This makes zinc a crucial indicator of global economic health. Zinc ranks as the fourth most consumed metal on the planet, after iron, aluminum, and copper. That alone tells you just how massive its importance is for the global economy and industry. Annual worldwide zinc production sits at roughly 12 to 13 million metric tons. These are enormous volumes, underscoring its irreplaceability across hundreds of applications. The primary zinc mining regions are China, Australia, and Peru. These three countries together account for a significant share of global zinc ore extraction, making them key players in the market. For instance, China isn't just the largest producer, it's also the world's biggest zinc consumer, reflecting its powerful industrial expansion. Other major producers include India, the United States, Mexico, and Canada. When it comes to reserves, the U.S. Geological Survey estimates global zinc reserves at roughly 250 million metric tons.
On top of that, there are what's called resource spaces, potential deposits that haven't been explored yet or aren't economically viable to mine right now. Those are estimated at over 1,800,000,000 tons. These numbers show that zinc, unlike some rare metals, will last for many decades, even with growing consumption. Most zinc is mined from underground operations, entire subterranean cities stretching hundreds of feet, sometimes several miles beneath the Earth's surface. These aren't just holes in the ground, they're networks of tunnels, shafts, ventilation systems, and hoisting shafts. It all starts with exploration. Geologists, like detectives, hunt for ore bodies, sections of rock where the concentration of zinc, which, by the way, usually occurs as sulfide ore, like sphalerite, and almost always comes with lead, silver, and sometimes copper, is high enough to make it worthwhile.
Once a deposit is discovered, mine construction begins. This involves sinking vertical shafts, which provide access to the ore, lift materials up, lower equipment down, and creating horizontal tunnels, or drifts, that lead directly to the ore veins. The actual ore extraction process? Dynamic, risky. Miners use specialized equipment, powerful drilling rigs that bore holes into the rock, called blast holes. Explosives get packed into these holes. After a carefully controlled detonation, massive volumes of rock shatter. It's like a spectacular earthquake, in miniature, under control. And that's how, starting from an underground explosion, through crushing into powder, through flotation with millions of tiny bubbles, through roasting at 1800 degrees and reduction at 2700 degrees, where the metal literally turns into vapor and vanishes into thin air, then condenses back into liquid zinc, a metal is born that shields steel from rust, makes bridges possible, cars, skyscrapers, without which the modern world would look completely different.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands. 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go.
Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood.
In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries.
Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70.
Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off.
The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible.
But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled.
Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries.
Steel cables were invented to replace ropes made from natural fibers. Ropes couldn't handle heavy loads. Chains were stronger but 10 times heavier. Steel cables solved both problems. Today, these cables hold up bridges, lift cranes, anchor oil platforms at depths of over half a mile. Diameter up to 21 inches. Weight 70 tons. Braking strength 9,700 tons. That's the weight of 50,000 cars. How do you make a cable that won't break? Today, you'll see the complete process, from a steel rod just 1/5 of an inch in diameter to a giant cable 900 feet long. If you want to see how thin wire transforms into a monster with a 10,000-ton braking strength, subscribe to the channel. Here we show you the industries that hold the world together. History. The modern steel cable was invented in 1834 by German engineer Wilhelm Albert. He developed it for coal mines. Hemp and manila grass ropes couldn't handle the job. The weight of coal in a cage? Over 3,000 pounds. Mine depth? Nearly 1,000 feet. Hemp rope broke from moisture and rubbing against shaft walls. Albert braided cable from steel wire. Wire diameter, just under 1/10 of an inch. 6 wires per strand. 6 strands around a core. Cable diameter, 3/4 of an inch. Strength, 5 times stronger than hemp. Lasted years instead of months. During the World War, steel cables anchored mines to the ocean floor. Deployment depth up to 300 feet. Water pressure, 150 pounds per square inch. A cable just over an inch thick held a 600-pound mine, plus current and waves. Today, steel cables are everywhere. Cranes, elevators, suspension bridges, drilling rigs, ski lifts. Wire drawing, it all starts with rod, a steel wire 5.5 millimeters in diameter. The rod is made from grade 70 to 80 steel. Carbon content, 0.7 to 0.8%. Manganese, 0.6%. This is high carbon steel, hard and strong. The rod unwinds from a coil weighing 2 tons. It's pulled through a drawing mill. This is a series of dies with holes of decreasing diameter. First die, diameter 4.8 millimeters. Second, 4.4. Third, 4.0. Fourth, 3.6. Fifth, 3.2. Sixth, 2.8. Seventh, 2.4. Eighth, 2 millimeters. 8 passes total. Each pass reduces the diameter by 10 to 15%. Between the dies are pulling drums. Drum diameter, 500 millimeters. Rotation speed, 300 revolutions per minute. Linear drawing speed, 470 meters per minute. That's 28 kilometers per hour. The wire heats up from friction. Temperature exiting the die, 200 degrees Celsius. Cooled with water. After drawing, the wire is hard. Tensile strength, 1800 megapascals. Elongation, 2%. It's brittle. Heat treatment needed. Heat treatment. Heat treatment. The wire gets heated in a furnace to 1650 degrees Fahrenheit. Hold it there for 20 minutes. The steel structure reorganizes. Carbon dissolves into the lattice. Then it cools in air at a rate of 180 degrees per hour. Slow cooling. You get tempered steel. Hardness drops, but ductility increases. Elongation, 8%. The wire's now flexible. Ready for rope making. Strand twisting. Take 6 wires, diameter 0.08 inches. Twist them around a central 7th wire. Lay length, 4 3/4 inches. That's the distance one wire takes to complete one full wrap around the center. Helix angle, 15 degrees to the axis. Twist direction, right hand. Looking along the strand, the wires spiral clockwise. You get a strand, diameter 0.24 inches. Starting wire length, 3,300 feet. Finished strand length, 3,100 feet. The difference, that's what the twisting eats up. The strand bends easy. Bend radius, 6 inches. Strand strength, 70% of the combined wire strength. losses from bending and friction. Rope stranding. 6 strands, 1/4 inch in diameter, twisted around a core. The core is organic. A hemp rope, 1/4 inch diameter. It's soaked in lubricant. Hemp is elastic. It absorbs shock loads. Stores lubricant inside the rope. There can be more strands. Standard construction is 6 by 7. 6 strands with 7 wires each. There are 18 by 7 ropes. 18 strands, 7 wires per strand. There's 36 by 7. More wires mean a more flexible rope. The diameter of a 6 by 7 rope with core 1/4 inch wires is about 3/4 of an inch. Breaking strength is 50 kilonewtons. That's 5 tons. Weight is about half a pound per foot. The rope gets wound onto a drum 6.5 feet across, 5 kilometers per drum. That's over 3 miles. Weight of the drum with rope is 8 tons. The ropes ship out to plants that make giant cables. Manufacturing giant ropes. United Offshore Services in the Netherlands makes ropes ranging from 4 3/4 inches to 21 inches in diameter. The factory houses a machine that's over 650 feet long. It twists finished ropes around a central core rope. Here's an example. They're making a rope that's 13 inches in diameter. They take 6 ropes, each about 4 inches thick, plus a central rope that's 4 3/4 inches. Then they twist them together. The rope spools get mounted on a rotating carousel. The carousel is nearly 40 feet across. It spins at 2 revolutions per minute. The ropes unwind from the spools. They pass through guide rollers. They twist around the central rope. The lay length is 71 inches. The lay angle is 20 degrees. Twisting speed is 11.5 feet per minute. In 1 hour, they produce 690 feet of rope. The finished 13-inch rope gets wound onto a spool that's 13 feet in diameter. Breaking strength? 9,700 tons. That means this rope won't snap until you load it with 9,700 tons. Marking and lubrication. The cable gets marked along its entire length with different colored paints. Red section, the start. Yellow, the middle. Blue, the end. Every 33 feet, a marker with a number. Then they lubricate it. They use lithium-based grease. Drop point temperature, 356 degrees Fahrenheit. The grease protects against corrosion and reduces friction between the wires. The cable runs through a bath of liquid grease heated to 176 degrees. The grease soaks into the core and between the strands. Then they apply an outer layer, anti-corrosion coating. It's a thick paste made from paraffin and corrosion inhibitors. Coating thickness, 0.02 inches. The final cable, length 558 feet, diameter 13 inches, weight 76 tons, breaking strength 10,700 tons. They move it with a crane rated for 165 tons. One end gets hooked. They lift. The cable hangs vertically. Lift height, 164 feet. You need a tower. At the factory, there's a tower 197 feet tall, specifically for this. Super long ropes. Hendrik Vader Group in the Netherlands makes the longest ropes in the world. Length, 920 feet. Diameter, 16 inches. Different technology. The machine travels along rails 1,000 feet long. At the start sit spools of rope. 8 spools. On each, a rope diameter 10 inches, length 920 feet, weight 110,000 pounds. Strength of each, 7,700,000 pounds. The machine starts moving. Speed, 6.5 feet per minute. The ropes unspool. They twist around a central rope diameter 10.25 inches. Lay length, 6.5 feet. The machine travels 1,000 feet in 2.5 hours. You get a rope diameter 16 inches, length 920 feet, weight 440,000 pounds. Strength, 31 million pounds. That's the weight of 80 tanks. At the end, they make a loop. They bend the rope back 15 feet. They splice the free end with the main rope. You get a loop 15 feet long. Loop diameter, 5 feet. The splice is locked with steel clamps. 10 clamps. Each clamp, 2 steel half cylinders. Tightened with 8 M36 bolts. Torque, 590 foot-pounds. Transport and deployment. A rope 900 feet long, weighing 440,000 pounds, lies coiled on the factory floor like a snake. It needs to be loaded onto a ship. They use 3 forklifts, each rated for 55,000 pounds. They lift the rope at 3 points. Drive it to the dock. Distance 1,600 feet. Speed, half a mile per hour. Time, 30 minutes. At the dock stands a crane rated for 880,000 pounds. It grabs the rope by its loop, lifts it, lowers it into the ship's hold. The ship carries the rope to Norway, to the Åsgard oil and gas field in the North Sea. Sea depth, 980 feet. A floating production platform sits there. Platform weight, 110 million pounds. The platform is held by 8 anchors. One rope 16 inches in diameter runs to each anchor. Each anchor weighs 440,000 pounds. Sits on the seabed. The rope runs from the anchor to the platform. Rope tension, 2 million pounds in calm weather. In a storm, 6.5 million pounds. Safety factor, 5 times. The rope is rated for 20 years of service. Inspected every 3 months. They send down an underwater vehicle with a camera. Inspect every foot. Looking for broken wires, corrosion, wear. If wear exceeds 10%, they replace the rope.
Every year, the world extracts over 8 million tons of gray, unremarkable ore. But only a tiny fraction of it undergoes an incredibly complex, almost alchemical journey to become a metal capable of withstanding even spaceflight. Titanium isn't just a metal. It's a substance born in hell from fire, chlorine, and magnesium at temperatures exceeding 1,000 degrees Celsius. Its first form looks like light ash, but from it they create the invisible skeleton of aircraft, eternal implants, and rocket engines. How does a chunk of dirty rock transform into a material stronger than steel yet lighter than aluminium? Watch to the end, and you'll see how an ordinary stone passes through chemical purgatory to become the heart of modern civilization. The history of titanium is the story of a ghost metal that remained hidden in plain sight for decades. In 1791, British clergyman and amateur geologist William Gregor, while studying black sand on the Cornish coast, discovered traces of an unknown element within it. But only 4 years later, in 1795, the great German chemist Martin Klaproth independently discovered the same element and named it titanium, after the mighty Titans from ancient Greek mythology. However, despite its thunderous name, the metal remained elusive. For nearly a century and a half, it slumbered in chemistry textbooks, resisting attempts to isolate it in pure form. Only in the 20th century, thanks to breakthroughs by American chemist Matthew Hunter and Dutch scientists, did humanity finally manage to touch pure titanium. From the mid-20th century, with the onset of the Cold War and the space race, titanium transformed from a laboratory curiosity into a strategic material. The United States, recognizing its colossal potential, invested enormous sums into its production. Titanium became the foundation for the legendary spy plane SR-71 Blackbird, capable of flying at the edge of space, and found its place in the construction of Apollo spacecraft. Titanium production begins with mining its ores, ilmenite and rutile. These minerals are found in the sands of Australia, Canada, and South Africa. After extraction, the ore undergoes multi-stage enrichment. It's washed, screened, separated from waste rock using magnets and gravity, yielding a dark, heavy concentrate. But this still isn't metal. This is merely titanium oxide, where it's firmly bound to oxygen. To break these molecular shackles, the concentrate is sent to chemical hell, into fluidized bed reactors. Here, at temperatures of 1,000 degrees Celsius, gaseous chlorine is blown into a boiling layer of ore and coal. A fierce chemical reaction begins. Chlorine tears titanium away from oxygen, forming a volatile compound, titanium tetrachloride. This caustic, toxic substance is then repeatedly distilled, purifying it from impurities to near-perfect purity. The next stage is the heart of the entire process, named after its creator, William Kroll. Into a sealed steel sarcophagus filled with inert argon gas, molten magnesium is placed. Then purified titanium tetrachloride is slowly fed in. A chemical duel begins. Magnesium, being a more reactive metal, literally rips chlorine atoms away from titanium. As a result of this battle, pure titanium settles at the reactor's bottom, but in the strangest and most unremarkable form imaginable. This is sponge titanium, a porous, lightweight gray mass that looks like frozen foam or pumice. It's brittle and utterly unlike strong metal. But inside this ugly porous sponge lies all the future might. This sponge is extracted, crushed, and then pressed under enormous pressure into dense briquettes. And only then is it sent to its final transformation, into the melting furnace. To transform sponge briquettes into a monolithic ingot, they're melted in vacuum arc furnaces. This is necessary because at high temperatures, titanium absorbs oxygen and nitrogen from the air with incredible greed, instantly making it brittle. Inside a sealed chamber, a powerful electric arc, like lightning, melts the briquettes, and liquid titanium flows into a copper, water-cooled mold. To achieve perfect uniformity, this process is repeated twice, sometimes even thrice. The result is a gleaming, silvery ingot of pure titanium, ready for further processing. Just look at this incredible transformation, from porous, lightweight sponge to dense, shining metal. But pure titanium is merely the beginning. To create materials for aviation and space, it's transformed into alloys. To molten titanium, like spices in a chef's dish, other metals are added. Aluminium for lightness, vanadium for strength, molybdenum for heat resistance. Thus is born, for example, the most famous titanium alloy, T6Al4V, which became the workhorse of the aerospace industry. These alloys are remelted several times to achieve perfect uniformity. The next stage is mechanical processing. Giant ingots are heated red hot to make them malleable and sent under presses or rolling mills. With incredible force, machines bend the metal to their will, transforming it into sheets, rods, beams, and wire. From these semi-finished products, the most complex parts are then cut, turned, and milled. But that's not all. In recent years, additive technologies, or three-dimensional printing, have entered the game. Special printers sinter the finest titanium powder layer by layer with lasers, growing parts of such complex geometry that traditional methods cannot achieve. This allows creation of lighter and stronger components for aircraft and rockets, saving up to 40% of weight. Every finished part undergoes the strictest control. It's X-rayed, scanned with ultrasound, checking for the slightest internal defects. In aviation, titanium has become indispensable. From it, they make up to 15% of a modern passenger airliner's weight, landing gear, wing elements, and of course, engine components. This significantly reduces the aircraft's overall mass and increases its fuel efficiency. In the medical field, roughly 70% of all implants, such as artificial hip joints or dental prosthetics, are made from titanium. Its unique biocompatibility means the human body doesn't reject it, allowing bone tissue to literally grow into the implant surface. This is a metal that becomes part of a person. Thus, having passed through fire and chemistry, an unremarkable stone transforms into high-tech material that pierces the heavens, explores space, and restores people's ability to move. But titanium conquered not only the sky, but also the darkest ocean depths. At the height of the Cold War, Soviet engineers created something unthinkable: submarines of Project Lyra, known to NATO as Alpha. Their hulls were made entirely from titanium. This allowed them to dive to depths unreachable by the enemy and develop underwater speeds exceeding those of torpedoes. These goldfish, as they were nicknamed for their incredible cost, became underwater phantoms, invulnerable to magnetic detectors and capable of escaping any pursuit. Titanium is the only material capable of withstanding the colossal pressure at depths of 800 meters whilst remaining sufficiently light. Moreover, its absolute resistance to corrosion in salt water makes it an eternal material for the marine element. So what's titanium's main secret, promised at the beginning? It's not just its strength or lightness. Its true magic lies in its ability to self-heal. Every time titanium's surface is scratched, it instantly reacts with oxygen from the air or water and covers itself with the thinnest, invisible, yet incredibly strong film of titanium oxide. This is a sort of invisible armor that instantly regenerates when damaged. It's precisely this film that makes it absolutely inert, preventing it from reacting with the human body or aggressive environments. But this superpower has another side, another secret. During mechanical processing, if proper technique isn't followed, fine titanium swarf can spontaneously ignite. This white fire burns at such high temperatures that it's impossible to extinguish with water or sand. Taming titanium is playing with fire in the literal sense, and only those who've mastered this art can make this mythical metal serve humanity.
Every year, the world produces over 100 million cubic meters of MDF boards. Picture this: if you laid them out as a road 30 feet wide, you could wrap it around the entire planet at the equator, and that's every single year. But few people know that these perfectly smooth panels aren't born from wood, but from trash, sawdust, scraps, and old newspapers. How does ordinary dust transform into a material that revolutionized the furniture industry? And what secret lies in a process where steam, resin, and hundreds of tons of pressure turn chaos into perfection? Stick around till the end. You'll see what's hidden behind every gleaming piece of furniture in your home. The base for MDF isn't solid logs, but what used to be considered trash: sawdust, wood chips, scraps, and even old waste paper. It's a triumph of resource efficiency. These mountains of wood waste arrive at the factory and first get thoroughly cleaned. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't about cleanliness. The steam is there to soften lignin, nature's glue that holds wood fibers together. Now begins the most critical stage, the one that sets MDF apart from its rougher cousin, particle board. The prepped softened chips get fed into a machine called a defibrator or refiner. Picture two giant metal discs, like millstones, spinning toward each other at incredible speed. Their surfaces are covered with an intricate pattern of sharp ridges and grooves. the wood pulp gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't chips anymore. It's something like fluffy, damp cotton or wood flour. We've just deconstructed wood down to its basic building blocks. Next, this fibrous mass needs to be dried, but it has to happen fast before the fibers start clumping together, so they get blown into a long, hot drying tube. A stream of hot air catches the fibers, and as they fly through this tube, all excess moisture evaporates out of them. And right here, while the fibers are still hot and swirling in this vortex, the next critical stage happens: resin application. A fine mist of binding agent gets sprayed into the airstream through special nozzles. This is urea formaldehyde resin, our glue. This mist coats every tiny fiber, covering it with a thin, sticky film. It's an incredibly efficient method, guaranteeing perfectly even glue distribution. Interesting fact, urea formaldehyde resin was first synthesized in the 1920s, but it only started being used on a massive scale in wood panel production after World War II. Now this resin-saturated, dry, and fluffy light mass is ready to become a board. It goes into the forming machine. The stream of fibers settles onto a wide-moving conveyor belt, forming a thick, loose, and perfectly even mat. Special rollers compress it slightly, and giant knives cut it into pieces of the required length. It already looks like the future board, but for now, it's just a thick, soft mattress of wood fluff. And then comes the climax, hot pressing. This loose mat rolls into a giant press. It might be either a multi-story press that simultaneously compresses an entire stock of boards, or a continuous press that looks like giant caterpillar tracks. And here, two powerful forces act on our mat at once. First, colossal pressure. The press plates squeeze our loose mattress with a force of hundreds of tons, reducing its thickness several times over and forcing out all the air. The wood fibers squeeze together tightly, creating an incredibly dense structure. Second, high temperature, 400 degrees Fahrenheit. This heat does two things. It activates the resin, causing it to polymerize and bond the fibers into a single monolith, and simultaneously evaporates any remaining moisture, which escapes from the board as hissing steam. After just a few minutes in this steel embrace, the loose mat transforms into a solid, dense, perfectly flat, and still very hot MDF board. Pressure in modern presses can reach 700 pounds per square inch. Imagine an adult cow standing on an area the size of a postage stamp. After pressing, the hot boards can't just be stacked. They need to cool down to relieve internal stresses. They're placed in a special fan cooler that looks like a giant card catalog, where they slowly cool down, fanned by air. Once the sheets have cooled, it's time to give them that finished look. First, they're stacked in tall piles and left to rest for a few days. This stabilizes their internal structure. Then each sheet runs through a sanding machine. Picture a giant belt sander with multiple heads. Wide abrasive belts strip away a thin surface layer from both sides, bringing the sheet to a perfectly precise thickness, say 16 or 18 millimeters, and creating that famous paper-smooth surface. And the final touch? Cutting. Massive saws slice the large production sheets into standard commercial formats. After that, every batch goes through strict quality control. Density, strength, thickness, and surface quality all get checked. Modern MDF panels have a density of 37 to 50 pounds per cubic foot. That's 1.5 times denser than natural pine. The finished, perfectly smooth panels get labeled, packed up, and shipped off to furniture factories, where they'll become the foundation for elegant and stylish pieces in our homes, silently demonstrating what a noble journey ordinary wood dust can take. The global MDF market? It's a giant machine churning out more than $25 billion a year. And this machine isn't planning to stop. Forecasts say it'll grow 6% annually. That means demand for this smooth material is absolutely insane.
So, who's the head chef in this kitchen?
The undisputed king, China. They produce over 50% of all the MDF in the world. Chinese factories run around the clock, turning out millions of cubic meters of boards for domestic use and export. But Europe's no slouch either, with powerhouses like Germany, Poland, and Turkey cranking out millions of cubic meters of high-quality board. German manufacturers are especially famous for innovative technology and strict environmental controls. Now let's talk volume. Every year, the world produces about 100 million cubic meters of MDF. That number is so massive, it's impossible to picture. Let's try anyway. Imagine a road. If you took all that MDF and laid it out as a road 30 feet wide and 10 inches thick, you could wrap a belt around the entire planet at the equator. Generously, an endless stream of material transformed into furniture, doors, and panels for our homes. What's fascinating is that MDF has unique properties you won't find in natural wood. No knots, no cracks, no voids. You can mill it, creating complex decorative elements that would be impossible or way too expensive with solid wood. That's exactly why MDF became the #1 material for kitchen cabinet doors, raised panel doors, and decorative trim. Plus, MDF holds fasteners incredibly well. Screws grip far more securely than in standard particle board. And that smooth surface? Perfect for paint. It goes on evenly, no fuzz, no grain, creating a finish that looks like plastic or even glass.
Environmentalists often criticize MDF for using formaldehyde resins, but modern technology allows manufacturers to produce E0 and E half grade boards, where formaldehyde emissions are lower than in natural wood. And so, having journeyed from a pile of sawdust and scraps through a steam bath, defibrator, pressing under hundreds of tons of pressure, and final sanding, this amazing material emerges. Dense, strong, perfectly smooth, and ready to become part of our homes. From humble kitchen cabinets to luxurious carved facades, from simple interior doors to intricate decorative panels, MDF works everywhere, the silent hero of modern interiors. It doesn't demand admiration, doesn't seek glory, but it's what makes our homes cozy and beautiful. And now you know its story, from trash to treasure, from wood dust to a masterpiece of engineering.
Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems, known as Christmas trees, that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world.
What if I told you that inside the most dangerous machines on the planet lies a steel secret that can only be created once, and a single mistake costs an entire nation? That there's an ingot that cools underground for 6 weeks and withstands pressure that would crush mountains? This giant is born in fires exceeding 2,700 degrees Fahrenheit, endures months of forging, strikes of tens of thousands of tons, and thermal shocks that would blow ordinary metal to bits. In 2015, a British company, Sheffield Forgemasters, poured 607 tons of molten steel into a giant casting pit. That's nearly the weight of a full passenger Airbus A380. After cooling, the ingot weighed 320 tons. To forge these giants, they use presses with a force of up to 40,000 tons. The energy for heat-treating ingots over a 2-week cycle can exceed 100,000 kilowatt-hours. That's the annual consumption of dozens of ordinary households. Stick around till the end. You'll find out what these monoliths are actually made for and why. Without them, the modern world would simply grind to a halt. Picture a massive foundry floor at a steel mill. This is where it all begins. To get a monolithic ingot, you need liquid steel of flawless quality, poured into a mold in one continuous stream. This stage demands maximum coordination. We're talking thousands of degrees and hundreds of tons of metal. A striking example of such an engineering feat was the record pour carried out by the British firm Sheffield Forgemasters in 2015. The company's metallurgists successfully managed the casting of 607 tons of liquid steel into a giant casting pit. To put that volume in perspective, it's nearly the weight of a full-sized Airbus A380 passenger jet. The pouring process is critically important. The steel must not only be melted, but also purified to a level meeting the strictest customer requirements, for reactor components, for instance. That means minimizing impurities, gases, and slag. Continuous casting ensures there won't be any layered defects or boundaries in the ingot structure that would compromise its mechanical strength. During casting, the steel must be degassed as much as possible. Oxygen and nitrogen content is controlled at levels that often don't exceed 20 parts per million. Excess gases can cause microvoids to form inside the monolith during cooling. Right after pouring the liquid metal, which can exceed 2,700 degrees Fahrenheit, time becomes the critical factor in this process. Unlike small castings that can be cooled quickly, a steel giant weighing hundreds of tons cannot be cooled rapidly. If cooling happens too fast, it'll lead to massive internal stresses, cracks, and structural defects, because the outer layer will solidify while the interior is still liquid. To ensure uniformity in the crystalline structure, the 607-ton ingot was left to cool in the casting pit for 6 weeks. This is a controlled, extremely slow process during which the steel gradually solidifies, dropping to a temperature of around 2,000 degrees. This slow crystallization allows the metal to avoid unwanted phase transformations and guarantees high-quality macrostructure, which is the foundation for the future component's strength. Only after this lengthy solidification period ends is the steel monolith, which, after shrinkage and removal of the defective top portion, weighs roughly 320 tons, carefully extracted from the ground. The ingot pulled from the earth, despite its weight, is not yet a finished blank. It has a cast, coarse structure with large crystals. To transform it into strong, homogeneous metal capable of withstanding extreme loads, forging is needed. Forging 500-ton ingots requires hydraulic presses with working forces from 10 to 20,000 tons. For instance, forging the largest reactor components uses presses rated at 40,000 tons. Before forging, the ingot is again carefully heated in special furnaces. This process can take weeks to ensure uniform heating throughout the entire volume of metal. The forging itself happens on giant hydraulic presses capable of generating tens of thousands of tons of pressure. The press breaks up large, brittle cast crystals. The pressure compresses the metal, eliminating microscopic voids that may have formed during casting. The metal develops a directional fibrous structure, significantly increasing its strength, toughness, and fatigue resistance. The forging process for such an ingot takes several months. It's a constant cycle of heating, pressing, rotating, and reheating. Every press stroke is a precise calculation aimed at achieving the required internal geometry and mechanical properties. The energy needed to maintain the heat treatment furnace for ingots during a 2-week cycle can exceed 100,000 kilowatt hours. That's comparable to the annual electricity consumption of dozens of typical households. During heat treatment, the allowable temperature variation throughout the furnace can be just 70 degrees Fahrenheit, which requires highly precise multi-zone control systems. After shaping the ingot comes heat treatment. This is the final, critically important stage for tuning the internal structure of the steel. The multi-ton steel monolith, which just endured months of casting and forging, is like a clumsy giant whose final character hasn't yet formed. It's strong, but its internal structure is still chaotic, full of invisible internal stresses. The first stage is normalization, or as they say, homogenization. The idea is simple. We essentially stir the metal structure so it becomes absolutely uniform throughout its entire volume. This is done so that at every point in the blank, both at the surface and deep inside, the steel has identical properties. It's like evening out the temperature in an oven so the cake bakes perfectly. Then comes the most dramatic moment, quenching. The blank is heated to very high temperature, bringing it to peak plasticity. And then, suddenly, but under strict control, it's cooled. This could be a water or oil bath. This nature shock transforms steel's soft structure into the hardest, strongest form possible. It gives the part its core fighting power, but there's one side effect. The metal becomes brittle like glass, and massive internal stresses appear. If you leave it like that, it could crack from the slightest impact. That's why the final and most humane stage is tempering. The blank gets carefully reheated, but this time to a significantly lower temperature. The goal isn't to change the strength, it's to release those internal stresses that built up during rapid quenching. Think of it like a deep exhale after stress. It boosts the steel's toughness, making it impact-resistant and load-bearing, eliminating the brittleness. Only after successfully completing this full month-and-a-half cycle of character hardening is the steel ready to become part of a reactor or a giant press. But what are these steel giants actually for? These things we've invested so much time and resources into. They become critically important components in industries where the cost of failure is unacceptably high. Take nuclear power, for instance. These ingots become critical components in high-pressure reactors. Picture this. Pressure, temperature, and radiation demand absolute reliability. No seams, no welded joints that might fail. Just one solid monolith capable of handling extreme stress for decades. In heavy machinery, these giants become bed frames for the world's largest presses. These presses shape automotive frames, aircraft parts, and ship components. A bed frame that won't deform under thousands of tons of load, it has to be cast in one piece. And then there's power generation. Rotors for massive steam turbines or crankshafts for enormous marine engines that propel supertankers and container ships. These components need guaranteed resistance to bending and secondary loads. Only steel produced through this incredibly complex process can deliver that. And just like that, after pouring 607 tons of molten steel at 2,700 degrees Fahrenheit, through 6 weeks of slow underground cooling, through shrinkage down to 320 tons, through months of forging under 40,000-ton presses, through strikes of tens of thousands of tons, through normalizing, quenching, and tempering over 6 weeks, through consuming 100,000 kilowatt-hours of energy, a steel monolith is born, a single seamless giant capable of withstanding pressure that crushes mountains, temperatures that melt ordinary metal, and radiation that destroys all living things. This monolith becomes the heart of a nuclear reactor, the bed of a giant press, or the rotor of a turbine driving a supertanker. Without these steel giants, nuclear power plants would grind to a halt, ship engines would fall silent, and aircraft parts production would cease. Each ingot like this isn't just a chunk of metal. It's the result of incredible engineering precision, months of painstaking work, and millions of dollars in investment. And mistakes here are unacceptable, because the price could be too high for an entire nation.
Today we're at a facility they don't exactly advertise, but one the modern world can't live without. I'm standing in front of a massive complex where they produce TNT, that explosive material that blasts through rocks and quarries, sends rockets into the sky, and, when necessary, strikes back at the enemy. Everything here smells like chemicals, metal, and that industrial power that sends shivers down your spine. The territory stretches hundreds of yards in every direction. Concrete walls, pipes, tanks, and above it all, a low but constant hum of reactors. Let's walk through together. I just got my access pass, and we're heading into the production floor. Hold on tight, it's gonna get intense. TNT, or trinitrotoluene, showed up back in the 19th century when chemists started experimenting with toluene, a colorless liquid you get from coal or petroleum. 166 years ago, a German chemist named Julius Wilbrand heated toluene with a mix of acids and got a yellow crystal that detonates with monstrous force. Since then, TNT became the king of explosives, stable, powerful, won't blow up from impact or fire, only from a detonator. You can drop it, heat it, shoot it with a rifle, and nothing happens until a blasting cap goes off. That predictability is what made it indispensable. 1 gram of TNT, that's the benchmark unit for measuring explosive force, the standard all other substances get compared to. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant vessels made of stainless chromium molybdenum steel, because regular steel gets eaten away by acids in a matter of weeks. They pump in a mixture of nitric and sulfuric acids, concentrates that'll melt right through gloves. The reactor temperature is kept around 195 to 212 degrees Fahrenheit. Hot enough to keep the reaction going, but not so hot that it spins out of control. The nitration process happens in stages, taking anywhere from several hours to several days. First, you get mononitrotoluene, then dinitrotoluene, and finally trinitrotoluene, TNT itself. At each stage, another nitro group latches onto the toluene molecule, and with every step, the stuff gets more and more explosive. The acids circulate in a closed loop because they're regenerated and reused, not just dumped into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything stays locked down because the slightest slip and the reaction could go sideways. From the reactor, the mixture flows into coolers, long coiled tubes where the hot TNT crystallizes. Then it's into settling tanks. The heavy TNT sinks to the bottom while the lighter acids get skimmed off. What you're left with is a jelly-like mass, crude TNT, still damp with acid. It gets washed with hot water at around 160 to 175 degrees Fahrenheit to neutralize what's left. The water changes 3 times. The first run comes out yellow with acid, the second is cloudy, and the third is clean as a tear. The spent water doesn't just get dumped. It's neutralized with lime and holding pools, filtered through a sand layer about 10 feet thick, and only then sent to treatment facilities. Ecology stays under control because acid is poison to anything living. Meanwhile, the crystals get unloaded. The mass is already solid, but still 6 to 10% damp. Now comes drying, one of the most fascinating stages. The vacuum drying chamber, a room where rotor drums hum, each about 6.5 feet in diameter. TNT gets loaded in batches of 200 pounds. They seal the drum, pump the air down to a pressure around 4 inches of mercury, and fire up the heat to 130 to 140 Fahrenheit. Fans push warm air around inside. The drum rotates, crystals tumble, dry evenly, no sticking to the walls. 2 hours, and out comes pure yellow powder at 0.5% moisture. Skip this step, and TNT would clump together or go unstable from the dampness. The powder color ranges from light yellow to deep orange, depending on purity. Here, they're producing top-grade stuff, 98% pure. Next up, granulation. They moisten the powder, press it into matchbox-sized bricks under about 3,000 pounds per square inch. These bricks come out hard as rock. Then they crush them in hammer mills, where shafts spin at 6,000 revolutions per minute, turning the bricks into granules between 1 and 3 millimeters in diameter. Why granules? Because they're easier to pack, don't create dust, and detonate uniformly. The dust gets sucked out by ventilation because breathing in TNT is bad news. The granules get poured into sealed crates holding 100 pounds each. That's the standard for quarries and the military. Every crate gets checked for moisture, no more than 0.7%. Otherwise, the TNT starts to sweat and becomes sensitive. There are special molds for underwater charges too. The pellets get mixed with paraffin so they don't get wet. The crates are sealed, labeled by batch, and sent to storage. From here, the TNT heads out to quarries, mines, military bases. One crate is enough to blast through 200 tons of rock. Now, about safety, because without it, they wouldn't last a day here. The plant is divided into zones. Reactors sit inside concrete shelters at safe distances from each other, with anti-detonation barriers between them, about 50 feet high, made of reinforced concrete. The logic is simple. If one reactor blows, the barrier absorbs the shock wave and keeps the detonation from jumping to the next one. No open flames, no sparks. They even hand over their cell phones at the entrance. All electrical equipment is explosion-proof, lights sealed in airtight housings. Personnel wear anti-static clothing, shoes with conductive soles so static doesn't throw a spark. Every 5 minutes, sensor checks for gas leaks. Emergency showers and CO2 fire extinguishers everywhere. Were there incidents? In the 19th century, explosions wiped out entire factories, but now, 0 accidents in the last 10 years. Why? Because of automation. Computers shut down the reactor in seconds at the slightest anomaly. One operator at a console monitors 10 processes simultaneously. Compare that to the old factories. Back then, everything was done by hand. TNT was packed with bare hands. Explosions happened regularly. Now, robotic manipulators, sensors, cameras. Evolution. Let's look inside the lab. This is where they test every batch. A sample gets placed in a bomb chamber, a thick-walled steel cylinder. They detonate a milligram and measure the detonation velocity, around 22,600 feet per second. If the velocity is below spec, that means there are impurities in the batch, or the crystal structure is compromised. Then they check stability. Heat it to 200 degrees Fahrenheit, drop it from 10 feet, it shouldn't crack or detonate. Then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, you're good. Lab techs check purity with a chromatograph. Toluene or acid traces, not allowed. Production here is massive, 1,000 tons per month. Power comes from their own gas turbines and steam boilers. Waste? They regenerate the acids, redistill the toluene, send it back into the cycle. Filters on smokestacks 200 feet tall. Wastewater cleaned until it's crystal clear. Nearest town is 10 miles out, so no complaints from the neighbors. Interesting fact, TNT isn't just for blowing things up. Melt it at 180 degrees Fahrenheit, it turns liquid like hot wax, and pour it into shell casings. Or mix it with other compounds for plastic charges. In quarries, 1 ton shatters a boulder the size of a 3-story house. In mining, you can't drill a mile-long tunnel without it. In the military, it's the backbone of torpedoes, mines, and aerial bombs. I'm standing in the granulation shop right now. Hearing the press rumbling, watching granules pour into bins like golden sand. The air's clean, but there's that distinct chemical smell, a familiar scent to anyone who's been inside plants like this. Discipline here is ironclad. 8-hour shifts, every action by the book, every step under camera. The people here are like jewelers, except they're not working with gold. They're working with explosives. The factory's like a living organism, roaring, spinning, producing power. TNT isn't evil. It's a tool. It builds roads, digs mines, defends the nation. Without it, there'd be no 1,000-foot bridges, no tunnels carved through mountain ranges. From the yellow crystal discovered a century and a half ago to today's high-precision production with robots and computers, it's been a massive journey. But the essence remains the same, turning chemistry into controlled force.
What if I told you there's a metal that flows like water at room temperature, killed thousands of workers during the colonial era, and without which gold mining would be impossible? A metal that vaporizes at 1100 degrees Fahrenheit and condenses back into liquid silver? Every year, the world produces around 1,300 tons of mercury, but that's nothing compared to historical scales. Over the last 500 years, humanity has extracted about 1 million tons of mercury from the Earth's depths. Half of that million was used before 1925. Mercury is obtained from red ore, cinnabar, by heating it to 900 to 1100 degrees Fahrenheit. During this process, mercury sulfide breaks down, releasing mercury vapors and sulfur dioxide gas. China dominates production, 95% of the world's mercury. In 2022, China produced 2,000 tons of mercury. A standard flask holds 76 pounds of mercury. These were the exact flasks used to ship it to gold mines during the gold rush. Stick around till the end. You'll discover a secret that even those who work with this metal won't talk about. Picture an underground mine somewhere in China, Kyrgyzstan, or Mexico, the world's biggest mercury producers. Deep beneath the surface, in the dim glow of miners' lamps, red streaks appear in the rock. This is cinnabar, mercury sulfide, a bright red mineral that humanity has known for thousands of years. The ancient Romans mined it both as a pigment and for mercury. The ancient Egyptians were using mercury as far back as 1500 BC. Greek philosopher Aristotle in 350 BC described how cinnabar was heated to extract mercury for religious ceremonies. Cinnabar forms in veins associated with volcanic activity and hot springs. About 90% of deposits require underground mining with tunnels. The remaining 10% can be extracted through open-pit methods. Cinnabar is separated from the surrounding rock through drilling and blasting or using powerful machinery. The ore is hauled out of the mine on conveyor belts or in trucks. Because cinnabar is a relatively concentrated ore, it can be processed directly without intermediate steps to remove waste rock. The ore is first crushed in one or more cone crushers. A cone crusher consists of an inner cone rotating on an eccentric vertical axis inside a stationary outer cone. When ore is fed into the top of the crusher, it gets squeezed between the two cones and breaks into smaller pieces. For concentrating low-grade cinnabar with a specific gravity of 8 to 8.2, gravity and flotation methods are used. Grinding to -48 mesh is the economically viable liberation point for the mineral. Some operations use mineral jigs to recover coarse heavy mineral and any metallic mercury that might be present in the ore. Flotation with one or more cleaning stages is used to produce a high-grade concentrate. It's not uncommon to obtain concentrates containing 40 to 50% mercury from ores containing 5 to 15 pounds of metal per ton. The concentration ratio is therefore high. The dewatered concentrate from flotation is combined and stored for roasting and recovery of metallic mercury. Now comes the most critical and dangerous stage, roasting. Cinnabar concentrate gets loaded into specialized furnaces. These can be multi-hearth furnaces, where ore mechanically moves down through a vertical shaft from one level to another via slowly rotating rakes. Or rotary kilns, where ore tumbles along the length of a long rotating cylinder, tilted a few degrees from horizontal. Either way, heat comes from burning natural gas or other fuel at the bottom of the furnace. Heated cinnabar reacts with oxygen in the air at temperatures ranging from 930 to 1,110 degrees Fahrenheit. A chemical reaction occurs. Mercury sulfide breaks down into sulfur dioxide gas and mercury vapor. Mercury rises as vapor. This is called roasting. Mercury vapors rise upward and exit the furnace along with sulfur dioxide, water vapor, and other combustion products. Significant amounts of fine dust from the crushed ore also get carried away and must be separated and captured. Next comes condensation. Hot gases containing mercury vapor pass through a cooling system. A condensation column is used, a special device where the vapors cool down and mercury condenses back into liquid metal. Pure mercury separates from sulfur in this process and evaporates easily. The condensation column collects the liquid metal. Thanks to mercury's high specific gravity, impurities gather on the surface and can be easily removed. The liquid mercury gets poured into standard iron flasks. Each flask holds 76 pounds of mercury. That's the standard unit of sale. These exact flasks shipped mercury to gold mines during the gold rush in California and Nevada in the 18th and 19th centuries. The process is simple in essence, with one drawback: toxic fumes. If roasting is done incorrectly, mercury vapors, which are highly toxic, can get released into the atmosphere. This was catastrophic for workers in the colonial era. The history of mercury production is full of tragedies. In 1564, cinnabar mining began in Huancavelica, Peru. With a local source of mercury, the amalgamation process was adopted for refining silver in Potosi, Bolivia, in the early 1570s. As a result, massive quantities of mercury were released into the environment. Between 1564 and 1810, approximately 17,000 tons of mercury vapor were released into the atmosphere in Huancavelica and 39,000 tons in Potosi. In 1604, an advocate for indigenous people described how fumes, dust, and candle smoke in the mine caused coughing and Huancavelica disease, and argued that forcing people to work in mercury mines meant sending them to a slaughterhouse. In 1630, a contemporary described the mines as a living image of death and a dark shadow of hell. The Jesuit José de Acosta, around 1590, wrote about the roasting process. If the smoke or fumes reach the people opening the pots, they get mercury poisoning and die, or are left in very poor condition or lose their teeth. The largest mercury deposit in history? Almaden in Spain. It was worked from Roman times until 1989, the world's biggest producer. In 2000, Almaden yielded 236 tons of mercury. Other major deposits: Khyder Khan in Kyrgyzstan, 550 tons, Algeria, 240 tons. During World War II, mercury production was critical. Mercury fulminate was essential for bullet primers, and the biggest producing region in Spain was under dictator Franco's control. The U.S. ramped up domestic production from 1941 to 1944. The price per flask during the war years averaged around $380 in 1960 prices. Today, global mercury production has plummeted. In 2016, they produced 4,500 tons, but in 2023, just 1,200 tons. China dominates with 95% of world production, 1,000 tons in 2023. Mercury has diverse applications, but its use is declining due to toxicity. Mercury easily forms amalgams with other metals, making it useful for extracting gold and silver. Much of the incentive to develop mercury deposits in the United States arose after the discovery of gold and silver in California and other western states in 1800. When mercury mixes with gold slurry, it triggers a reaction that separates gold from ore. This amalgam is then heated to vaporize the mercury and leave behind gold nuggets. Artisanal and small-scale gold mining is the largest source of anthropogenic mercury emissions, accounting for 38% of global releases. Other applications include chlorine and caustic soda production in mercury cell electrolysis plants. Until recently, this was a major consumer. In 2023, only one such facility was operating in the U.S. electrical devices: fluorescent and mercury vapor lamps, mercury batteries, switches, and relays. Measuring instruments, thermometers, barometers, pressure gauges. dental amalgam, a mixture of mercury with silver and other metals for fillings. But because of its high toxicity, mercury use has dropped sharply over the last 20 years. Inhaling mercury vapor is especially dangerous for the kidneys, central nervous system, respiratory and cardiovascular systems. Inhaling mercury vapor also causes neurobehavioral disorders like hand tremors and mental impairment. Exposure to other forms of mercury, particularly methylmercury, which accumulates in fish, can also lead to kidney problems, lung issues, and central nervous system damage, as well as arthritis, reproductive problems, memory loss, psychosis, and in some cases, death. The United States banned the export of elemental mercury on January 1, 2013, under the Mercury Export Ban Act of 2008. Global mercury resources are estimated at around 600,000 tons, mostly in China, Kyrgyzstan, Mexico, Peru, Russia, Slovenia, Spain, and Ukraine. And so, having traveled from red cinnabar ore through roasting at 1100 degrees Fahrenheit, through evaporation and condensation, through the tragedies of thousands of workers in the colonial era, through the gold rush and world wars, emerges a liquid metal that flows at room temperature, without which gold mining would be impossible, but which has killed more people than any other metal in human history.
Every year, the world mines thousands of tons of metals, but only one is so dangerous it can kill you even as dust, and yet helps us peer 13 billion years into the universe's past. That's beryllium, a metal lighter than aluminum but many times harder than steel, a metal without which the James Webb Space Telescope wouldn't exist. But there's one detail almost nobody talks about. Why does producing it feel like a chemical nightmare? And why does working with it become a deadly gamble? And what exactly are those factories hiding behind thick protective glass? Subscribe so you don't miss out. You'll learn something that'll forever change how you think about metal. Let's jump straight to the numbers because they're absolutely mind-blowing. Look at this block of metal. Appears to be just another gray hunk of iron, but try to lift it and you'll nearly clock yourself in the chin from the surprise. Beryllium has a density of just 1.85 grams per cubic centimeter. That's almost 30% less than aluminum, which we've always considered the gold standard for lightness. But here's the kicker. Despite being this lightweight, beryllium is 4 times stiffer than steel. Its elastic modulus hits an incredible 303 gigapascals. What that means is this material puts up insane resistance to any deformation. You could build a structure thin as paper, and it would still hold its shape under colossal stress. On top of that, beryllium has this exceptional ability to maintain its strength at high temperatures, making it absolutely irreplaceable in the aerospace industry. The extraction process, that's a whole chapter in the textbook of industrial survival. The primary source here is a mineral called bertrandite, mined in the deserts of Utah. The ore contains just 0.5% beryllium. To extract this metal, the rock gets crushed and dunked into sulfuric acid, turning everything into a chemical slurry. Then, through a series of complex manipulations with hydroxides and fluorides, they get pure beryllium fluoride. They mix it with magnesium in massive crucibles and heat it up to 2400 degrees Fahrenheit. The magnesium grabs the fluorine, and shiny metallic grains settle to the bottom, so-called pellets, or beryllium pebbles. Each grain is only a few millimeters across, but it's from these tiny pieces that parts for spacecraft and military hardware will eventually be assembled. But this is just the beginning, because working with them directly is impossible. And here's where we get to the most dangerous part of the tour. Beryllium is a genuine toxic bomb. Its dust causes chronic beryllium disease, which basically makes your lungs shut down.
All it takes is breathing in a microscopic amount of particles, and your immune system starts attacking your own tissues. The disease can show up years after exposure, when you've long forgotten that one day you spent at the facility. So nobody here pours the metal into molds like cast iron. Instead, they use powder metallurgy methods. Metal grains get ground into fine powder in special mills under vacuum. Every single dust particle has to be controlled. Then, they pour this powder into massive steel capsules and subject it to vacuum hot pressing. Imagine hundreds of atmospheres of pressure and temperatures over 1800 degrees Fahrenheit, simultaneously crushing this powder, forcing it to become a solid block. This goes on for hours until the structure becomes perfectly uniform. Why did the telescope engineers choose this hellish material for their mirrors? It's all about the cold of space. James Webb operates at Lagrange Point 2, about 930,000 miles from Earth, where temperatures plunge to minus 370 degrees Fahrenheit. Regular glass deforms unpredictably when it cools this much, expanding in one spot, contracting in another. But beryllium has a unique property. Its thermal expansion coefficient at low temperatures becomes virtually zero. It basically freezes in place. The shape stays constant no matter how brutal the cold gets. This made it possible to build mirrors that remain perfectly smooth even in the savage cold of deep space. Each of the 18 mirror segments measures 4.3 feet across but weighs just 44 pounds. If they were made from glass, each one would tip the scales at over 200 pounds, and the rocket simply couldn't lift off the ground. Each mirror was carved from a single block, removing 90% of the mass from the back to create a lightweight honeycomb structure. This is called lightweighting. The walls there are just a few millimeters thick. After that, polishing begins. It's done using computer systems that remove irregularities measured in nanometers. 1/1000th of a meter. That's the precision we're talking about here. If Webb's mirror were the size of the Atlantic Ocean, the biggest bump on its surface wouldn't be taller than a regular coin. Then the mirrors are taken to a cryogenic chamber, where they're cooled to space temperatures, microscopic warping is measured, and then they're polished again to compensate for those changes. This cycle was repeated dozens of times over several years. Now take a look at this color. We're used to seeing telescope mirrors in gold, but underneath that gold lies pure beryllium. The gold is only applied at the very end through vacuum deposition. The gold layer is just 100 nanometers thick. That's 1,000 times thinner than a human hair. The entire massive mirror, covering about 270 square feet, used only about 1.7 ounces of gold. That's like 3 or 4 wedding rings rolled out across a giant surface. Gold is essential because the telescope searches for infrared radiation from the very first stars that ignited 13.5 billion years ago. Beryllium provides rigidity and stability, while gold delivers perfect reflection in the precise wavelength range needed. At this facility, safety protocols look like paranoia, but it's justified paranoia. See those yellow lines on the floor? You can't cross them without special footwear. The air in the shop completely refreshes every 3 minutes. Beryllium levels in the air must not exceed 0.2 of a microgram per cubic meter. That's so small you couldn't even see it under a microscope. But sensors are everywhere. After every shift, each worker goes through a special shower, and their clothing gets disposed of as hazardous waste. That's the price we pay for the ability to peer into the depths of space.
But beryllium isn't just about space. Look at these tiny components for aircraft engines. Because beryllium conducts heat better than most metals, it's perfect for parts that need to cool down fast. Its thermal conductivity is around 210 watts per meter Kelvin. It pulls heat away faster than aluminum and doesn't melt until 1287 degrees. This lets planes fly faster and engines run more efficiently. Here's another wild fact you probably won't hear in chemistry class. Beryllium is almost transparent to X-rays. Take an X-ray through a steel plate, you'll see nothing. But with beryllium, the rays pass through like it's not even there. That's exactly why the windows in every X-ray machine and CT scanner at hospitals are made from beryllium foil. It lets doctors get crystal clear images of your body without losing radiation power at the machine itself. So what does all this cost? If you want to buy a kilogram of pure beryllium, expect to shell out anywhere from $800 to $1,000. But that's just raw material. The cost of a finished part can be 10 times higher or more because of how difficult it is to machine and all the safety precautions required. A single web mirror segment costs millions of dollars when you factor in all the years of testing and polishing. And even with these insane prices, global beryllium production doesn't exceed a few hundred tons per year. That's how rare and difficult it is to work with. Thanks for watching. Hit that like button if you love real science as much as I do. See you at the next classified facility.
Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of two glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s, when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred. Improvements to laminated glass and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between two glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection, special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements, thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment. Imagine if construction could be not just strong, but ultra-lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, Standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in saltwater. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation. a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal. What if I told you there's a metal that's 15 times rarer on Earth than gold, and to mine just 1 ounce of it, you need to process 10 tons of ore? A metal whose entire annual supply would fit in an ordinary room, while all the gold in the world would fill 3 Olympic-sized swimming pools? Every year, the world produces only 180 tons of platinum. That's 17 times less than gold. South Africa produces 120 tons, 74% of global production. Russia's in second place with 23 tons. To extract 1 ounce of platinum requires processing 10 tons of ore, while for gold, just 2 to 3 tons. The Merensky Reef, Upper Group 2, and Platreef contain only 2 to 10 grams of platinum per ton of ore. After flotation, the concentrate is heated to 1500 degrees Celsius to burn off iron and sulfur impurities. Then they use aqua regia, a mixture of nitric and hydrochloric acids, to dissolve the platinum. The concentration of platinum in Earth's crust is only 0.5 parts per million. Stick around till the end. You'll discover a secret that even jewelers won't tell you. Picture an underground mine several miles deep somewhere in South Africa, in the Bushveld province, home to the world's largest platinum deposits. These aren't open-pit mines. They're narrow tunnels blasted through rock up to 2 miles beneath the surface. Here, platinum is extracted from thin layers, reefs, that stretch for hundreds of miles but measure just 6 inches to 5 feet thick. 3 main reefs: the Merensky Reef, Upper Group 2, and Platreef. The Merensky Reef, discovered by Hans Merensky in 1924, has historically dominated global platinum production. Here, platinum reaches its highest concentration, 50 to 60% platinum group metals. Upper Group 2, a chromite-rich reef, more stable but with lower gold, copper, and nickel content. Platreef, a wider reef with lower platinum grades but higher base metal content, roughly 5 times more. Miners drill holes into the reef walls and pack them with explosives. After detonation, the shattered rock containing platinum and other metals is transported to the surface for processing. The ore gets crushed, then goes through flotation. That's a process that separates minerals based on how they stick to air bubbles in water. Mills grind the ore down until 60% of the particles pass through 75 micrometers. Then the ground ore gets mixed with water, and collector reagents are added, things like xanthates and dithiophosphates, which make the sulfide minerals containing platinum hydrophobic. Water repelling. Air gets pumped through the mixture, creating millions of tiny bubbles. The hydrophobic particles containing platinum stick to the bubbles and rise to the surface, forming a froth that gets skimmed off. Hydrophilic waste rock particles stay at the bottom. Platinum in Merensky ores is closely tied to base metal sulfide minerals: copper, nickel, and cobalt. The platinum group metals are present either as discrete platinum group minerals included in or attached to the sulfides, or in solid solution with the sulfides. The base metal sulfide minerals in Merensky: pyrrhotite, pentlandite, chalcopyrite, and traces of pyrite. After flotation, the concentrate still contains less than 1% platinum. Now, the concentrate heads to the smelter. It's dried and then heated in electric furnaces to temperatures exceeding 2700 degrees Fahrenheit. Air is blown through the molten metal to oxidize iron and sulfur impurities. Sulfur oxidizes to sulfur dioxide and gets removed as exhaust gas. Iron oxide is removed as phyllite slag. Platinum's melting temperatures are significantly higher than other metals due to the presence of chromium, which makes them incompatible and requires special furnace design. The power capacity of platinum smelting furnaces reaches 19.5 megavolt amperes and 68 megavolt amperes. Energy consumption runs 800 to 850 kilowatt hours per ton of concentrate. Platinum's high melting point means impurities like iron burn off, and the result is a powdery sludge of platinum group metals: rhodium, iridium, ruthenium, and osmium, plus platinum itself. The converter's slag phase contains significant amounts of trapped platinum metals and gets recycled back to the smelting furnace to recover those captured metals. The converter mat gets cooled down, crushed, and processed at a base metals refinery. Here, hydrometallurgical processes dissolve the copper and nickel, leaving behind a residue rich in platinum group metals. This platinum metals residue heads to a precious metals refinery, where various solvent extraction and precipitation methods separate out the individual metals. Getting pure platinum requires further refining. Typically, this involves aqua regia, a mix of nitric and hydrochloric acids in a 1:3 ratio. Aqua regia is one of the few acids that can dissolve platinum. When the concentrate is treated with aqua regia, the acid produces chlorine, which bonds with the platinum, forming chloroplatinic acid. The final step uses ammonium chloride to convert the chloroplatinic acid into ammonium hexachloroplatinate, which can be calcined to yield pure metallic platinum. Platinum content in the residue after hydrometallurgical processing can reach 5,900 ounces per ton. That's an enrichment of nearly 500 times compared to the original flotation concentrate. Now, a bit of history. In 1735, Antonio de Ulloa and Jorge Juan y Santasilia witnessed indigenous Americans mining platinum while the Spanish traveled through Colombia and Peru for 8 years. Ulloa and Juan found mines with whitish metallic nuggets and brought them back home to Spain. Antonio de Ulloa returned to Spain and established the first mineralogical laboratory in Spain and was the first to systematically study platinum, which happened in 1748. In 1783, French chemist François Chaboneau was the first to obtain a pure sample of platinum metal. In 1801, English scientist William Wollaston invented a method for efficiently extracting the metal from ore. Growing demand for the metal led to the discovery of major deposits in the Ural Mountains in 1824 and in Canada in 1888. This ultimately led to geologist Hans Merensky's discovery of the largest platinum deposit on Earth in 1924. Platinum is primarily used in automotive catalytic converters. In 2014, out of 218 tons of platinum sold, 98 tons, 45%, went to vehicle emission control devices. 74.7 tons, 34%, to jewelry. 20 tons, 9.2%, to chemical production and petroleum refining. 5.85 tons, 2.7%, to electrical applications like hard disk drives. The remaining 28.9 tons went to various other minor applications, such as medicine and biomedicine, glass-making equipment, investments, electrodes, anti-cancer drugs, oxygen sensors, spark plugs, and turbine engines. The most common use of platinum is as a catalyst in chemical reactions, often in the form of platinum black. It's been used as a catalyst since the early 19th century, when platinum powder was used to catalyze the ignition of hydrogen. In automotive catalytic converters, it completes the combustion of low concentrations of unburned hydrocarbons from exhaust gases into carbon dioxide and water vapor. Platinum is extremely rare on Earth, occurring at a concentration of just 0.05% in the Earth's crust. Platinum often occurs chemically unbonded as native platinum and primarily as an alloy with other platinum group metals. Most commonly, native platinum is found in secondary deposits among alluvial sediments. The alluvial deposits used by pre-Columbian peoples in the Chaco Department, Colombia, are still a source of platinum group metals today. Another major alluvial deposit is located in the Ural Mountains, Russia, and it's still being mined. When comparing the rarest precious metals by annual mine production, platinum is far rarer than gold. We're talking about more than 15 times rarer by annual output. In 2018, silver, gold, and platinum mine production totaled 860 million ounces, 108 million ounces, and 6 million ounces respectively. Producing a single ounce of platinum requires about 10 tons of ore. For comparison, gold needs around 2 to 3 tons of ore to produce 1 ounce, while silver takes 5 to 10 tons per ounce. Global demand for platinum in 2023 was estimated at 7.5 million ounces. The world's largest platinum producer, Anglo American Platinum, produced 1.75 million ounces of platinum in 2023. Russian company Norilsk Nickel produced 593,000 ounces of platinum in 2022. Every year, an additional 2 million ounces, yak 60 tons of platinum, comes primarily from recycling auto catalyst and jewelry. What makes platinum stand out is just how difficult it is to extract. Platinum mining is extremely labor-intensive. The KEL process represents a potentially significant improvement in platinum concentrate processing technology from an economic standpoint through dramatically reduced energy costs. Compared to matte smelting, electricity consumption drops by 82%, and overall carbon dioxide emissions decrease by 70%. And so, having traveled from a thin reef deep underground in South Africa, through blasting, crushing, flotation with millions of bubbles, through smelting at 1500 degrees Celsius, through dissolution in aqua regia, through precipitation with ammonium chloride and calcination, platinum is born. A metal 15 times rarer on Earth than gold, requiring 10 tons of ore to be processed for a single ounce, whose entire annual supply, just 180 tons, would fit in a single room. A metal that catalyzes chemical reactions, cleans the exhaust of millions of cars, and adorns fingers with jewelry that never corrodes. Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears, yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory, this is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace, and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine, a 100-foot-long monster. Here's where the